organizers for this opportunity to participate and also co-chair this session. And without taking much time, let me see if Dr. Pai is there. So Dr. Pai is a good colleague and friend. I've been working with him for a long time. So he is the head of the Office of Climate Research and Services at the India Meteorological Department, and he has got a great amount of experience in seasonal and other climatology areas. So over to you, Dr. Pai, to give your lead talk on seasonal variability and prediction of southwest monsoon rainfall over India. Over to you, Dr. Pai.
Okay. Thank you, Srinivasan. Are you seeing my presentation? Srinivasan?
Yeah, we can see your presentation, not yet in the slides mode. You can put it on a slideshow. Yeah, now it is okay.
Okay.
Go ahead.
Yeah. Thank you, Dr. Srinivasan. So this is outline of my lecture. First, I will be discussing on significance of southwest monsoon to the country, and then about different timescales of monsoon variability with an emphasis on interannual variability and its climate drivers. And then I will also discuss on various approaches used for operational seasonal prediction, starting from a brief history of monsoon forecasting in India, and then ending with the present operational seasonal forecasting system for southwest monsoon. And also, since we have introduced a new forecasting system this year, I also will present about the verification of the forecast issued for 2021 southwest monsoon, and end with the conclusions and future plans. Yeah. So you can see that this is a mean and standard deviation of seasonal rainfall during southwest monsoon. You can see that along the west coast, it is actually the pattern has got a significant impact due to orography. You can see along the west coast is the highest, and in the northeast you have got the highest rainfall, and in the eastern, central eastern part, because of low pressure system, you have got maximum rainfall maximum. But in the northwestern most and southeastern most part, the lowest rainfall. You know that for normal rainfall, as a country as a whole, we receive around 89 centimeter around. And among the monthly, July has almost 33% of the seasonal rainfall during July and 29% during August. And coming to the significance of southwest monsoon season, you can see here the contribution of seasonal rainfall to the annual rainfall for a various season. During the southwest monsoon, it contributes about 70 to 90% of the annual rainfall in most parts of the country, as well as even you can see the other parts of South Asia and other even eastern part of Asia also. You have got a large contribution due to southwest monsoon. During the post monsoon, at the same time, in the southern eastmost part and Sri Lanka, you have got some contribution due to northeast monsoon. And the monsoon rainfall also has got significant relation for the kharif and rabi crops in the country. In fact, more significant association with the kharif crop. Though the rainfall received during the monsoon also has got an impact on the crop production during the winter. At the same time, it also many studies particularly by Gadgil and Gadgil 2006 has shown that impact of severe drought on Indian GDP during the drought monsoon is very significant. Even even this is despite the substantial decrease in the contribution of agriculture GDP over last several years. And another important aspect of monsoon is that since it is significantly related to agriculture, and as of now, almost 50% of the labor force is in the agriculture sector compared to industry, which is 22%, and services 31%. Therefore, any impact on the monsoon will have a significant impact on the life and of population. Almost 50% of the labor force is directly or indirectly depend on the agriculture sector. Coming to various timescales of monsoon variability, all of we know that monsoon varies in all time scale, and the major time scale of variability of monsoon are diurnal, mainly caused by the changes in the convection and precipitation pattern during the day, 24 hours. And another type of variability is monsoon weather, which is a time scale of around 3 to 5 days, and mainly caused by monsoon lows and depression, tropospheric cyclone, west coast offshore trough, etc. And that actually produce short-lived local flooding, erosion, high winds, etc. Example is your Mumbai deluge during 26-27 July 2005, which are large flood type of situation in along the west coast, particularly over Mumbai region. And another type of variability is intra-seasonal, which is nothing but envelopes or clusters of weather events leading to 20 to 40 days of dry or wet periods, particularly over central parts of the country. And it is the most difficult variability to forecast, but perhaps the most important of all the time scale for economic and agriculture sector. And here I will be more concentrating on interannual variability, which are are the variations in the annual cycle of the monsoon caused by and producing below normal, above normal rainfall, and it is generally influenced by sea surface temperature variations associated with ENSO and inherent variability in the Indian Ocean, though other kind of climate divers also influence the interannual variability. Finally, you also have got a decadal variability, which as we know, Indian monsoon also exhibits significant decadal variability. Here I have just shown you pictorially various kind of variability. This is intra-seasonal, showing active and break conditions during a above normal year, that is 1994, and 2013, which is a normal year, and 2014, which was below normal year. You can see that year like a below normal years, you have got a long period of below normal epoch in the intra-seasonal variability, and at the same time above normal, you have got above normal type of epochs, envelopes in the above normal, but you have got almost equal in the normal year. This is kind of a decadal. We had a multi-decadal variability in the early part of the century, and then it turned to above normal, and then again in recent years we are passing through below normal decades. This is again reflected through an epochal variation of 31 years moving average of all India rainfall. You can see that currently we are passing through a below normal epoch. In spite of last 2-3 years, we are getting above normal years. It is expected that in the next few 5 to 10 years, we may continue to be in the below normal epoch, and then again there is a likelihood of we are moving to a above normal epoch. Coming to the interannual variability, you can see that long-term trend in that is almost missing. You don't find a long-term trend in the time series of all India. However, deficient monsoon during the 147 years, there were 22 deficient monsoon years and 22 excess monsoon years. Together, it is only explaining around 30% of the excess or deficient, which means that monsoon is a very stable system. With 70% of the years, we are getting a normal. So our concentration in forecasting is mainly basically when you have got a deficient and excess years. Though we know that even in the excess years, there can be several pockets of in the country which can be deficient or normal, and similarly during a deficient year there can be pockets of excess or normal years. And it is well known that major drivers of interannual variability are ENSO, Indian Ocean dipole, snow cover, etc. But there has been several studies which relate with other climate drivers also. But most of the studies, you will see that ENSO and IOD has got the most significant impact on the interannual variability, particularly ENSO. Therefore, in the next few slides, I will be concentrating on impact of ENSO on the Indian monsoon rainfall. So this is showing an interannual variability of ISMR for the period 1901 to 2021. You can see that many of the deficient years are related to ENSO, and many of the excess years are related to La Nina. However, there is a more association between El Nino and deficient years are much significant. That is 63% compared to the association between excess and La Nina, which is only 46, which indicates that it is not only the El Nino monsoon is more significant, stronger association, more stronger than the excess monsoon La Nina, and also that there are forcing other than SSTs over East Pacific that influence over the Indian monsoon. So we also should notice that there are many El Nino years in which monsoon was normal. A typical example was 1997, when El Nino, it was the very strongest El Nino during the century, but still monsoon was normal. And similarly, at the same time, there are years like 1979, when ENSO was neutral, still monsoon was deficient. This shows the 21 years moving correlation, which shows that there is a secular variation in this relationship. And during the early 2000s, we had a very weak relation between ISMR and ENSO, but in recent years, again, the relationship has improved. And this has been spoken by many lectures during this INTROMET itself. So I will not go more detail into that. So this is the special pattern, composite pattern of a rainfall over monsoon Asia during El Nino years and La Nina years. You can see that during El Nino years, we have in the country, major part of the country is division, and only in the northeastern part and even in the Myanmar region, you can see that above normal rainfall. In the maritime region also, you will see deficient rainfall, and many parts of the East Asia. Exactly opposite is the case of the La Nina. You have got above normal rainfall above majority part of the country. And here Myanmar, almost exactly opposite, and even in the maritime region also, you see the opposite relationship. Coming to IOD monsoon relationship, IOD is strongly depend on the state of the system, as we know, since it is in the Indian Ocean region, and therefore the monsoon circulation, variability in the monsoon circulation has got a significant impact on this IOD itself. So it is there is a strong feedback of both in the monsoon circulation and IOD circulation over the Indian Ocean. As a result, we find that though there is some type of association in some years, there is no significant statistical correlation between DMI and monsoon rainfall Indian, and in the Indian region. However, IOD and monsoon has got some common features like biennial variation, and also it has been found that IOD plays an important role as a modulator of the Indian Ocean rainfall, and it influences the correlation between the ISMR and ENSO, as shown by Ashok et al. In 2001. In fact, the IOD and ENSO was found to be complementarily affecting the ISMR, and it has been seen that whenever ENSO and ISMR correlation was low, IOD and ISMR correlation was high. So as I had shown you earlier, there was period when in last in around 2000, when there was a El Nino ENSO monsoon was weak, and at the same time the IOD monsoon relationship was much better than the other period. And coming to a composite pattern during positive IOD and the negative IOD, you can see that during positive IOD in the monsoon trough region above normal, but in the west coast there is not much difference between negative IOD. But in the leeward side of the Western Ghats, you can see in the opposite signature can be found, and in the similarly in the monsoon trough. But this feature is not only limited over the Indian region, even that can be seen in the maritime region as well as Myanmar region also. And next I will be discussing about various approaches that is being used for seasonal prediction of monsoon rainfall. Basically, there are three methods that are being used: empirical and statistical method, based on methods like multiple CCA, artificial neural network, etc. and that were being mainly used in IMD operational LRF up to 2000, up to last year. And that is basically based on historical observed data for the predictor and for the relevant predictors like SST, snow cover. So the relationship is, association is based on the statistical relationship. And then assuming that this relation that we identify remains in the future also, this method is being used. And another method being used is a dynamical method, basically, based on SST forced AGCM, which was previously very significantly was used, but currently we use coupled general circulation models, which are one-tiered systems, which predicts both ocean and atmosphere together. And example is monsoon mission CFS, which is one of the highest resolution model used for seasonal forecast anywhere in the world. And from this year, we also started a multi-model ensemble method, whereby several combination of coupled model forecast are being used to generate forecast, which was implemented in the IMD's present LRF system. And the third, which is a recent development, is a hybrid method, which are statistical rescaling of dynamical model simulation. Example is IIT Delhi ERPS, and also IMD Delhi also prepare a forecast using this method. In the team of Patnaik and his group prepares that forecast. Now I will move to history of the operational forecast in the country. You know that 1877-78, which was an El Nino, India actually, and China, in fact, faced a large famine. And modern research on, we can say that climate prediction began with this event, which had a severe impact on India and North China. You know that 1875, after establishment of IMD, its first director was H.F. Blandford. He was asked by the British company to prepare, seasonal forecast for the Indian monsoon. And he actually prepared a tentative forecast for the period for 82 to 85, based on relationship between winter and spring snowfalls over Himalayas and monsoon rainfall. And when he found some success during the testing period, he implemented it as tried to have an operationally given a forecast in 1886 for the country as a whole. And that was the best beginning of a seasonal prediction history in the world itself, in fact, you can say. And that was issued on 4th June. In 1892, actually, forecast for the second half of the monsoon was started. And, one of the most important development was by Walker, who introduced the concept of correlation of LRF. And the objective method was started during that time, when regression method was used for preparing the forecast. And you know that between 1882 to 2002, 16 parametric and power regression model by Taplial and group had implemented. There was a good success. And then in 2003, we actually implemented a two-stage forecasting system based on 8 to 10 parameter. So you will see that over the years, operational long-range forecasting system in India underwent many changes in its approach and scope. And in the recent history, you will see that it was in 2003, the first seasonal forecast model based on dynamical forecasting was implemented. And in 2007, based on the study of Dr. Rajivan et al., new statistical ensemble forecasting system was introduced. And in 2012, under a monsoon mission, coupled forecasting system was implemented. And in January 2015, seasonal forecast model was we started using for generating forecast for South Asia. However, subsequently we started using monsoon mission CFS model to replace SFM to generate forecast for South Asia, and as well as to prepare ENSO and IOD bulletin. And then the same model we started for temperature forecast in 2016 onwards. And as a experimental model to support the operational forecast, we implemented 2017 in IMD Pune, MMCFS. and operational forecast was started to support the SCFS. And in the last this year, we started MME of coupled models for monthly and seasonal forecast. That is a very significant impact, development. I will discuss a few slides on that subsequently. But however, I will just go through the models we used in 2007 to 2020, which is the seasonal, statistical ensemble forecasting model based on 8-parameter model. So this shows you, various skills of various forecast for various homogeneous regions and monthly forecast. You will see that the skill reduces with a smaller region and smaller period, that is monthly and bi-monthly. The skill decreases. However, there is a noticeable skill was found for seasonal forecasting and all India rainfall. You can see that between this period, we were issuing forecast in the 2 stages. In April, first stage forecast, and June, second forecast. And also in the second stage, we used to issue forecast for July and August rainfall, and subsequently update for the second half. In the late July, we used to issue for second half of the forecast, and then for seasonal forecast for homogeneous regions. So these are the 8 parameters we use for SCFS forecast. This is a schematic diagram. For April forecast, first 5 parameters were used, and for June forecast for the update, last 6 parameters were used, and SCFS was used based on 2 techniques, your multiple regression and as well as projection pursuit regression, and all possible models were created based on this various combination of this model, and the best few models were used to prepare the final forecast. So that is the method we used. And if you compare the forecast based on 2007 to 2020 based on SCFS, you will see that there was significant improvement in the skill. You will see that the during the period 2017 to 2020, there was only 6.61 compared to the earlier period of the absolute error of 6.61% of LPA compared to 14 years prior to that. That means almost 25% reduction in the absolute error. And also you will see that correlation of the forecast, operational forecast was 0.42 in the recent years compared to minus 0.47. So which shows that there was significant improvement in the skill of the seasonal forecast based on the SCF statistical ensemble forecasting system. However, the issue was that many we were not giving a spatial distribution of rainfall. So that is what the users and various government authorities were asking
Dr.
for.
Pai, we are running out of time, so
yeah. I will
thank
quickly
you. Just to allow some questions and all. Thank you.
Yeah.
Sorry for rushing.
Yeah, no problem. So we this year we implemented new strategy based on MME, based on which we not only give a quantitative forecast, we also started to issue spatial variability, spatial distribution of rainfall also, and also we started to issue specific forecast for core monsoon zone and rain-fed region, which was most important for agriculture and also for homogeneous region. This is just showing how MME is being implemented. Basically, we generate based on MME, we generate quantitative and probabilistic forecast. And these are the models used for generating the MME forecast. And you can see that MME has got a better, lower absolute error compared to the SCFS and CFS2 or MMCFS, and both for the April and June forecast. And this is the verification of the LRF for this year. You will see that except for Central India, when we are forecasted above normal, more than 106%, whereas the real was 104. And June and July and August, when there was a slight difference from our forecast, but otherwise most of our quantitative forecast, probabilistic forecast was in very much accurate actually. And this is just I am rushing through spatial pattern also. This is for seasonal rainfall pattern. In the left side, observed rainfall category, and this is the forecast for all India, seasonal forecast. This is for June, July. You can see that many areas of below normal was predicted, and August also you can see that in the many central India below normal rainfall was predicted well, and September you can see that central India large above normal rainfall was predicted, though exactly spatial distribution has not been predicted well, but many of the areas we could predict well. And in addition to the monsoon forecast, we are also issuing various this type of forecast for the national and regional forecast. And this is just example for South Asia rainfall, maximum temperature and minimum temperature we have issued for this year. And this is for northeast monsoon. You can see that normal to above normal rainfall predicted for the southern peninsula in many parts. And this is the last slide. Actually, you can see that IMD provides various seasonal forecast over India and South Asia. However, there is a significant improvement in the seasonal prediction, but seasonal forecasting over smaller region and the spatial distribution has to be further improved. We are planning to develop MME tools for generating LRF products for India and other South Asia for all the season of the calendar year with a monthly update. And it is also planned to develop tools for impact-based seasonal forecast. Thank you.
Thank you. Thank you very much, Dr. Pai, and sorry for rushing you. Of course,
no issue.
Thanks for, very detailed and excellent presentation on the operational aspects. Of course, it is a very challenging area, but since we have just about the total time, maybe we may not be able to take any questions at this point. Maybe later in the chat box or something we can carry on. So thank you again for the presentation, and then we will move to the next talk. So the next talk is by Dr. Rajiv Batla from the Banaras Hindu University. He works on monsoon diagnostics and other areas alike. So he will be presenting on accessing the changes of climatic extremes over the Indo-Gangetic plains using observations and model simulations. So over to you, Dr. Rajiv Batla.
Thank you, Dr. Srinivasan, and I thank to organizers to invite me for this talk. So just I'm sharing my slides. Is it visible, sir? Slide is visible?
Yes, it's visible. You can put it on slideshow mode.
Yeah.
Thank you.
Sure. Now it's okay?
Yeah, it's okay. Excellent. Go on.
Just.
So are you okay, Rajiv?
Just a minute.
Okay. Yeah, it's moving.
It's not moving, but. Okay, sir. Thank you very much. So I have today the topic of my talk is assessing the climatic extremes over Indo-Gangetic plain using observation and model simulations. So as all of are very well aware that climate is nothing but the average of the 30 years period, and it is the average of weathers. And climate change, we have three categories: climatic variability, climate change, and paleoclimatology. So changes from 10 years to 100 years and more than thousands years. And the climate variability is different between two seasons from same region, from year to year variation, and climate change is longer time scale and paleoclimate for the last year. So this is the climate change impacts. As we all know that climate change impact on health, agriculture, water resource, coastal areas, species and natural areas. So a lot of works are going on this impact study. So I have chosen the topic on regional scale, that is Indo-Gangetic plain. And that climate change over Indo-Gangetic Plain and associated with extreme weather events, frequency and intensity of disasters. So first, I have done my study on variability of Indian summer monsoon over Indo-Gangetic Plain and its relation to El Nino and La Nina. So what we have used, that the data used for 7 meteorological subdivision, which covers the IGP regions, that is Gangetic West Bengal, Jharkhand, Bihar, East UP and West UP, Haryana, Punjab, for the period of a long period of 1871 to 2012 for the monsoon season. And this data is taken from the IITM site. And El Nino La Nina years we have taken from 1901 to 2012, and it's obtained by NOAA site. So this is the criteria for describing the drought and deficient, normal, excess and flood years, IMD criteria. The drought is less than -1.28 and deficient -1 to -1.28. This is the criteria. So we have seen the climatic variation in SMR over IGP. So these are the some statistical parameters which is calculated over period of 1871 to 2012 over the region of studies. And this is we have done for the 30 years period and for the whole period. So these are some statistics we have produced. These are the trend for tricadal trend over the 4 tricades. We have divided whole of the period into 4 tricades, and we are seeing that the trend is increasing. But recent tricades from 1883 to 2012, we are finding that the rainfall is having some decreasing trend over the recent tricade. Similarly, we are the decadal variation also we have calculated for the different decades. For the last 3-4 decades, we are seeing every decades it is having some decreasing trend. The recent 4 decades. Now these are the variability of the monsoon rainfall for different tricades and decades over in the IGP region. Then we have interrelated this trend with the El Nino and La Nina events over India. So these are the La Nina years. So we have 7 La Nina years. This is the normalized rainfall. And this is the characteristic of monsoon over IGP regions. So we can see it is very clearly shown that whenever La Nina occurs, every year is having either wet or flood years over Indo-Gangetic Plain, except 2010, which shows drought years. So this is exceptionally showing that 2010, it is La Nina years, but it is showing that it is a drought year over IGP. But most of the cases, it is showing either flood or wet years. So these are some statistics we have produced for the decadal variations. So this is also some previous decades and recent decades. We have already shown that last 4 decades we have having decreasing trend. I think this is not harm. So based on the drought and flood years, based on the criteria, we have defined some drought and flood years. So these are the drought years. Out of 23 dry years, we have 16 drought years. And out of 24 wet years, we have 13 flood years were identified over the period of studies. And first, we have already shown that what happened when La Nina occurs. Then we have again calculating what is the impact of El Nino years on the Indo-Gangetic Plain. So if we see except 1953 and except 1953, we have whenever El Nino years occurs, all our IGP experiences the drought years, except 53 and 1997, in which 1953 IGP experienced flood years, and in 1997 it is wet years. So most of the cases when La Nina occurs, it is associated with wet or flood years, and El Nino occurs, it is associated with drought years over IGP. So we have drawn some conclusion over for this study that 142 years period under the study consisted 24 excess monsoon, including 13 flood, and 23 deficient monsoon, including 16 drought years. And there exists a reasonably strong teleconnection between El Nino events and poor performance of monsoon over IGP. Whenever drought occurs over IGP, 63% of them are associated with the occurrence of El Nino events. And however, La Nina events are associated with wet monsoon years only in 22% of the cases, while a majority of 74% cases are associated with normal monsoon, showing La Nina conditions are weakly teleconnected to wet monsoon. So decadal variation in SMR over IGP shows bias toward below normal performance during recent 4 decades. And the frequency of drought and flood years has been increased in recent decades 2003 to 12. So these are the conclusions. So we have studies after this interannual and interannual variability associated with El Nino La Nina events. We have going for the climatic extreme, that is heat wave, cold wave, and extreme rainfall events over IGP for different studies. So these are the different, these are the examples of the recent events of climatic extremes over whole of the world. And these are the some exceptionally heavy rains in India and metro cities, which already taken from the records. This is Mumbai, Delhi, Kolkata, Bangalore, Chennai. So these are the extreme rainfall events occurred. So we have again chosen the Indo-Gangetic plain for our climatic extremes. I have already told Indo-Gangetic plain covers these regions of 7 meteorological subdivisions. So we have first studied the extreme rain events, then heat events, then cold wave events. So I am coming first for the extreme rainfall events. So first, this is the criteria. This is a data we have taken from the IMD, all data, temperature data and rainfall graded data from the different periods. For rainfall, we have studied period is 1901 to 2010, and heat wave and severe heat wave we have studied for 1963 to 2013, and cold wave and severe cold wave for 1951 to 2013. So first we are showing the results we have found for extreme rainfall events over IGP in changing climate during the last 110 years. So these are the criteria, IMD classification, different classification. We have again regrouped for this study non-rainy days and category 1, category 2, category 3. We have regrouped all these criteria into 3 categories. And we have calculated for dry spells, prolonged dry spells, short rain events, prolonged rain events also we have calculated for the area of studies. We have already published these results in JESS. These are the data and methodology we have chosen. Daily data, as I told you, we have taken from the IMD, analysis of dry spells, prolonged dry spells, short rain events, prolonged rain events, and a linear trend analysis also been carried out. And we have also test the significance for Mann-Kendall statistics. So these are the region. We have divided into 3 boxes. These are the 6 boxes. We have divided whole of the regions. box A, box and B, C, D, and E, F. So these are the study for the June category, and for category 1, category 2, and category 3, which we have regrouped from the IMD classifications. So we can find that category 1 rainfall, that is 2.5 millimeter to 64.4 millimeter a day, which shows that a slight increase is found in the month of June in the area of study, whereas category 2 category 2, that is 64.5 to 124.4 millimeter a day, has remained fairly constant. And while in category 3, which is nothing but the rainfall greater than 124.5 millimeter a day, has showing decreasing trend over Indo-Gangetic Plain in the month of June. So same analysis we have done for July and August and September. So if you see all the 4 months, we are finding that category 3 rainfall is showing decreasing trend over June and July and August and also in September. So this is overall view for the June, July, August and September for the category 1, category 2 and category 3. And this is the for category 1, category 2, category 3, we have that is for each month. Then we have also found that category 1 increases, category 2 also remains fairly constant, and over June, July and August, it is showing that it is a decreasing trend. So for each month and season, we have found that if the rainfall occurs for more than 124, means extreme rainfall events, heavy rainfall events, it's showing decreasing trend over Indo-Gangetic Plain. So it is not necessary that extreme rainfall events is increasing over the whole of the India. It means it is showing in each regions. So and then we have also studied the category-wise decadal analysis of the rainfall. So during the recent decade 2001 to 10, category 1 rainfall increases for the decades and not for the whole period. And for category 3 also it is so. Over whole of the period, if it is taking composite, it is showing decreasing, but for recent decade it's showing increasing trend. So again, we have calculated, as I told you, that we have calculated for dry spell, prolonged dry spell, short rain events, and prolonged rain events. It shows that dry spell events have remained unchanged. Prolonged dry spells, prolonged rain events, and short rain events having decreasing trends over Indo-Gangetic Plain. And this is the decade-wise analysis of the different spells, and which shows that dry spells have increased during recent rate. Prolonged dry spell also having decreasing trend over recent decade, and short rain events also have showing decreasing trend, and prolonged rain events does not show any regular pattern. So out of this study, we have conclude that the intensity and occurrence of extreme rainfall events over IGP showed significant decreasing trend for category 2 and category 3, and rainfall events except category 1 rainfall event which showed increasing rainfall frequency. So short, moderate rainfall having more increasing trend. It also found that decrease in frequency of category 3 rainfall event is more dominant than category 2 rainfall event. And heavy rainfall occurrence is most probable during onset months of monsoon, that is June and July. The decreasing trend of heavy and very heavy rainfall events might be associated with decrease in wind strength at 850 hectopascal over southern Bay of Bengal. And dry spell and prolonged dry spell remain more or less constant over the Indo-Gangetic Plain during the period of study. And then we have studied for the heat wave. So heat wave is defined as prolonged period of hot weather which may be accompanied by high humidity, and it is most common in summer. So in the present study, I told you we have already taken the IMD data, temperature data from 1963 to 2013 for the pre-monsoon month, March to June, and linear trend analysis also, and decadal also we have done, tricates also we have done, and statistical significance we have done for the, and we have taken some stations over Indo-Gangetic Plain, that is Chandigarh, Delhi, Calcutta, Purulia, Ranchi, Dhanbad, Patna Gaya, and Kapurthala, Ludhiana, and Varanasi, Gorakhpur, Agra, and Kanpur. So these are the 10 stations we have studied for the 50 years heat wave. So these are the criteria for severe heat events, and this is for heat wave events. So criteria for severe heat wave events is when normal maximum temperature of station is less than or equal to 40 degrees Celsius and departure of day's maximum temperature from normal is 7 degrees centigrade or more. And when normal maximum temperature of station is more than 40 degrees centigrade, departure of day maximum temperature from 6 degrees centigrade or more. So when normal mean temperature, it is for heat wave from 5 to 6 degrees. So these are the two criteria we have studied for March, April, May, and June. The heat wave are observed in Kapurthala and Gorakhpur station during the month of March. And in May and June, the frequency of heat and severe heat wave was increased for stations like Gorakhpur, Varanasi, Agra, Kanpur, and Delhi. So these are the 14 stations of IGP, which shows that during the stations, the heat wave trend is showing increasing trend over these stations, and severe heat wave showing that severe heat events increasing over the Chandigarh, Delhi, Calcutta, except Purulia and Ranchi, Dhanbad. So these are the variation of heat and severe heat wave over 7 regions of IGP. So for 7 regions of IGP are found to be increasing for regions as I already showed in table, that is in pictorial form. And this is decadal trends over the different decades, over the different stations. During the decadal study, it is found that the frequency of heat and severe heat wave has increased in the recent decades. So these are the conclusions we have drawn from the heat wave events. Maximum number of heat waves and severe heat waves are observed during the month of June and minimum during the March and April. The increasing trend of heat waves and severe heat waves are observed in Kapurthala and Gorakhpur stations of IGP. In May and June, the frequency of heat and severe heat waves has increased for stations like Gorakhpur, Varanasi, Agra, and Kanpur, and Delhi. And for yearly variation of heat and severe heat wave over 14 stations over the period, so the trend is found to be increasing for stations like Agra, Varanasi, Gorakhpur, Gaya, Kapurthala, and Ludhiana. And 7 regions of IGP heat wave and severe heat waves are found to be increasing for these regions like Punjab, Haryana, Chandigarh, and so studying the overall trend of heat wave and severe heat wave over whole IGP, it is found that trend of heat wave is decreasing while the trend of severe heat wave is increasing. Again, we have studied for the cold wave events over the regions.
I think Dr. Rajiv.
Yes. Okay, I will conclude. Okay, no problem. Within 2 minutes.
Thank you. Sorry for rushing.
No problem. So these are the criteria which is given by the, these are the months we have studied for the calculation of the cold wave events over the region. And month of January, the frequency of cold wave event has been abruptly increased more than twice the severe cold wave frequency. And for the month of February, cold wave events is more than twice the severe cold wave, but overall frequency of less than this. So this is combined effect of for the DGF season. The combined effect of cold wave and severe cold wave frequency is seen, whereas the cold wave is more than 4 times the severe cold wave events. So this is studied for the decades, and I'm not. So for the different months also we have shown that for different boxes we have calculated. So I'm coming to the conclusion for this. So on the basis of cold wave studies, that month of November experienced less cold wave and severe cold wave while in the month of December it is large number of events is found and it is increasing trend, and Feb month severe cold wave is declining, and from December to February DGF due to high frequency of cold wave severe cold wave event, the study region experienced the human loss and human activities are affected badly in these days of over IGP. And now we are doing for the, I have time, Srinivasan?
Already you have exceeded the time.
Okay. Sorry,
Dr.
so I am not
Rajiv.
covering the modeling aspect. I have covered the this observations. We have already doing this studies is completed and we are going to submit. We are calculating the extreme rainfall events over IGP. This is model we are for a codex domain, and we have only on region of India. We have calculating over IGP region. We are calculating for historical and near future for RCP 8.5 and IMD rainfall observations model. We have already run over IGP using Rexium. We have already validated, and I'm not going for detail because short of time. So I'm just concluding that Rexium 4.7 with all considered forcing data set has performing satisfactorily in simulating various category of rainfall events over IGP. And projected changes in all category of rainfall events reported moderate to higher increase, except rather heavy events during both the future and future time scale. We have different time scales. So large variations in result of these stations suggest the importance of micro scale studies by Wilbanks and Cates 99 also argued for a bottom-up approach, that is how local places contribute to global climate change instead of top-down approach. Therefore, along with large-scale circulation, regional and local changes may have played a crucial role in influencing the observed climate in a given area. The micro-scale studies are also helpful in working out of a proper mitigation and sustainable development plan of a given place. Thank you.
Thank you, Professor Batla. I think very interesting, and particularly the last statement which you made is very relevant of how we need such Indo-Gangetic plain level or even other levels for understanding these extremes very well. And also you pointed out that the heavy rainfall behavior is different in the IGP. That is interesting also. And sorry, don't have time, but there is one question which you may respond over the chat box. Devika has raised a question about IOD having any influence on the drought of particularly 2010. So you can respond over the chat box, but we will go. Thank you very much for your interesting presentation and go to the next one. Thank you, Professor Batla. You can stop sharing the screen so that we can go to the next presenter. And I have the pleasure of now inviting Dr. Anupam Hazara from IITM for presenting his work on understanding the role of deep convection on the seasonal monsoon rainfall over India. Over to Dr. Anupam. Thank you. Anupam, we can see your slides. Please go ahead. We can't hear you. Dr. Anupam, we cannot hear you. Your mic.
Is it, could you please hear me?
Now it's okay. Yes.
Now it's okay?
Yeah,
Okay,
now it's
fine,
okay.
fine,
Thank
fine.
you.
Okay, thank you. Thank you. First, I would like to thank you, organizer, for inviting me. In Intromet 2021, the title of my topic is basically deep convection and seasonal monsoon rainfall. So, firstly, I would like to acknowledge all collaborators, my student Usnangsu and others. So, the deep convection and the formation of the clouds is very important in terms of the time scale, as well as the formation and complex interaction between the aerosols also. And there are multiple interaction between the microphysics, deep convection, radiation, and dynamics to sustain the monsoon. So first we'll give the little background why we need the skillful ISMR prediction. As you know all, that agriculture, food production, and economy critically depends on the monsoon rain. And the skillful seasonal forecast has potential for high impact on agriculture as well as water resource management. So as you know that deficient and excess monsoon have a great impact on economy, as already discussed by many talk. So therefore, a reliable forecast of monsoon rainfall on the subseasonal to seasonal time scale is very, very important. So next is that what is the coupled climate model? So Wang et al. 25 have shown that coupled global land, atmosphere, ocean model is essential for the simulation of ISM climate. Rajivan et al. 2012, they have shown the scale of present generation model higher than the earlier generation model, which is reported by Krishna Kumar et al. 25, and which give an indication that improvement of the model lead to improvement of the skill, which is basically the ray of hope. However, it remained a grand challenge. Even today, all model is rather limited. So then what is the strategy? So select a prediction system involving a coupled GCM and make a systematic improvement of the physical processes. Here I particularly will talk about the microphysical processes. And the improvements of the coupled GCM will be targeted to improve the deficiency or biases of the model in simulating ISMR. So I will start with a schematic which is available in the Saha et al. 2019 JGR, unraveling the mystery of Indian summer monsoon prediction. So the schematic diagram illustrating the newly discovered association of large-scale predictor represented as giant octopus with a subseasonal component like the synoptic, lows, depression plus meso of the Indian summer monsoon. And you know that the predictor consists of all natural modes of variability, that is ENSO, IOD, PDO, NAO, snow, soil moisture, etc. And each represents an arm of the predictor. And the two long arm of the predictor aiming towards the synoptic and meso indicate the influence on the subseasonal process. With this cartoon, or with this schematic, we can start our hypothesis. And before that, as we know that it is already reported by Mule 1973 and then Sikka 1977 that majorities of lows and depression initiate over Bay of Bengal and move towards the central India, which contributes to about 45 to 55% seasonal ISMR as reported by Woon and Chen 25. As you know that during the monsoon depression or any other synoptic activity, the stronger vertical velocity will help to uplift more moisture below freezing level to form the supercool cloud water and then cloud ice and then snow and group via several microphysical processes like condensation, deposition, freezing, and rhyming, etc. It further invigorates the clouds by releasing radiant heat during thermodynamical phase changes and effect on dynamics. On the basis of this hypothesis, the outlines of my talk is the role of convection and ice phase processes on ISM, and then variance of ice mixing ratio and mean of cloud fraction during ISM, and what is the present status of the climate model and the model development. Finally, I will end up with the skill with the modified model. So why microphysics? Why deep convection? So it is shown by observation, particularly satellite observation, left is the Calypso, is showing that this is a fraction of raining clouds, and top is the ice phase, then liquid phase, and then ice plus liquid phase. One can see that the ice phase in the raining cloud is higher. Same thing has been shown in CloudSat data as reported by Field and Hempsfield 2015. And you can see then JJA, nearly 45 to 50% rainfall is coming from the snow melting, which indicates the importance of the deep convection and formation of the cloud ice. Now, if we see the deep convective cloud amounts over South Asian region or Indian monsoon region, bigger monsoon region, one can see the this is the JJ's mean deep convective cloud amounts from the ISCCP, and which can also see the same thing that the more deep convective cloud was in Behead Bay of Bengal and entered into the central India. And if we double check that deep convection counts for JJs per year, it also from the CloudSat, it's also telling the same story, and it is also verified with the cloud optical depth from ISCCP and cloud optical thickness from the MODIS. Now, what is the ice phase? So what is the status of ice hydrometer in the deep convection? So this is the ice phase in the high cloud fraction from the Calypso. One can see that the presence of ice phase is very, very stronger, which is again revealed by the cloud optical thickness ice from the MODIS. So all this suggests the presence of deep convection and ice mixing ratio is important for the sustaining the monsoon and the rainfall. Now, if we look into the mean and variance, the right ray panel is the mean of JJ's mean of rainfall from GPCP trim and cloud ice. One can see they are co-located. So now if we calculate the variance in different time scale, like 3 to 7, like synoptic variance, then 10 to 20, the QBM variance and MESO variance 30 to 60. So one can see the synoptic variance of ice mixing ratio and rainfall is stronger, followed by QBM and MESO. So the synoptic is very, very important for the formation of the ice as well as the rain. So now one can see the total cloud fraction, and this is the high cloud fraction. So both are different platform like ISCCP, Calypso, and GeoCCP we have taken, and one can see that high cloud fraction contribute to more in the total cloud fraction. And this is well known, the monthly variation of total cloud fraction from ISCCP and Calypso, May to October, and one can see the JJ's period, the cloud fraction is higher. Now, what is the status of the model? So if we look into the climate model, most of the model underestimate in simulating the cloud fraction, total cloud fraction, as compared to observation. Observation is the lower. So then what about the CFS? I am talking about the Cloudpool forecast system. At IITM, we are using Cloudpool forecast system for the development and for the prediction system, as already mentioned by Dr. Pai in the first talk. So one can see the original model of CFS B2 or control. This is also underestimating the total cloud fraction, similar to the all other CMIP model as compared to observation. So if we modify the microphysical process, the second panel, it shows that total cloud fraction simulate reasonably very well as compared to observation. So now question is that how it impact on the rainfall. So you can see the underestimation of the cloud fraction, total or high level cloud fraction, giving a overestimation of convective to total rainfall ratio, means too much convective rain and too little stratiform rain, which is coming from the ice and mixed phase processes. So similar thing happened for CFS B2 also. Now, what is the status of the model in CFS B2? So we have introduced now, modified the microphysical scheme in CFS B2. We have also done the partitioning of cloud water and ice in the convective scheme. Also, the improvement has been done in the explicit feedback between the large scale condensation and cumulus parameterization. We have done so many sensitivity experiment, and then we can see that how the improvement of high cloud fraction is seen from the control to the improved version as compared to the observation. Similarly, the convective to total rainfall ratio also improved from the control to the modified version. So the details are available in the GEMS recently published 2021 and other in 2017. So now I will come to the what is the relation between these ice. We are talking about the ice mixing ratio with the global SST. So what is the teleconnection? So MIRA2 is the, as you know, the MIRA2 is the reanalysis data. So we first compare the product of MIRA2 with the Calypso high cloud fraction. Calypso is the satellite data. This is the teleconnection of Central India average high cloud fraction with the global SST correlation. So both are showing the similar pattern, Calypso and MIRA2. So we safely use the MIRA2 data for ice mixing ratio. So right panel is the ice mixing ratio with correlation with ice mixing ratio averaged over Central India with the global SST. So top is the MIRA2, bottom is middle is the CFSV2 control, and bottom is the CFSV2 modified microphysics. So one can see that the modified microphysics of CFSV2 improve and the pattern of the teleconnection. So now question is that how it improves. So as we propose in our hypothesis and as we shown before that this is the track of cyclone, depression, lows, and this is also reported by Mule 1973 and Sikka 77. And most of the rainfall contributes, or nearly average 50% rainfall is coming from this. So now what about in the model? So we check the spatial variation of this lead lag composite of 3 to 7 days filter ice mixing ratio during JJS. The shaded is the cloud ice and contour is the rainfall. So, and the maxima of the synoptic event signify the lag 0. So one can see the an evident westward propagation and escalation over Head Bay of Bengal and Central India. So two box we have choose for calculating the time series. One is the BOB box, another the Central India. So one can see very nice propagation in MIRA2, which is captured in the modified microphysical scheme. So now, last question is that this development of the mean and the synoptic event, how it impact on the scale. So whether it manifests in the scale. So now I will show you that the scale, what is the scale of the model. The scale of the model with modified microphysics scheme jumped from the 0.56 to 0.71. The details is available in Sahitar 2019 JGR, unraveling the mystery of Indian summer monsoon prediction, and it improves the predictability limit also. So, and the detailed microphysical scheme is placed here, and where the different color, original, modified, and newly added tendency equations are putting in different colors. So one can visit, one can see that 2017 GEMS and 2021 GEMS. So detailed development are listed there, you can find. And here with this, I will conclude with the major findings or summary. First, the synoptic variability contributes maximum to the ISMR anomaly. The synoptic and MESO are not noise, but part of the predictive signal. In comparison to the global effort on subseasonal to seasonal prediction, the ISM is the unique case of unified and predictable system on synoptic 2-decadal time scale. Then the proper representation of cloud convection in synoptic time scale are essential for the seasonal mean ISMR. The finding also reveals that mean and synoptic scale variance of the cloud hydrometers, particularly cloud ice, is linked with the slowly varying forcing like ENSO. And the sensitivity of the model simulation using coupled forecast system with modified microphysics clearly demonstrate the support of the model development activity based on new observation and reanalysis findings. With that, I thank you all. And
Thank you, Dr. Anupam Hazara. I think a very interesting study. Thanks for sharing excellent results. So I think we have just 1 minute. If we have any questions on the chat box, rapporteurs, can you see if there are any questions? Because we have. So I think there are none. So thanks again, Dr. Anupam, for sharing that
Thank
very
you.
nice, interesting study on improving microphysics. It's very, very crucial. So thank you, all the presenters. And I have now the pleasure of handing it over to my co-chair, Dr. Satyamurthy, as I have to take leave for some other session. So Dr. Satyamurthy, over to you. Thank you very much. So Satyamurthy, you are still muted, I think. I'm sorry, I think there is some problem.
Sir, Dr. Satyamurthy is not available.
Yeah, okay. So maybe I will have the opportunity to pleasure actually. Milind is a good friend from several years. So I have the pleasure of inviting Milind Majumdar to present his study on monitoring field scale soil moisture variations in the monsoon environment. Over to you, Dr. Milind.
धन्यवाद डॉक्टर जी श्रीनिवासन जी. नमस्कार जी. I will be presenting now about this monitoring of field scale soil moisture variations in monsoonal environment. The associates, we have many associates actually, our PhD student, project scientist, colleagues, and internship students, Professor S.N. Patil from North Maharashtra University, and our mentor, Dr. R. Krishnan. Main thing is the recent study and this IPCC report have brought out that the land region is more vulnerable to climate change in the earth ecosystem. For example, significant rise in land surface temperature, land degradation, desertification, soil erosion, etc. So the thing is here, what I want to highlight is soil moisture among the land region also, or land processes also, land atmosphere interaction also. Soil moisture is an important component of the hydrological cycle, as it influences land atmosphere interaction through exchange of surface fluxes. Interestingly, this memory time scale, the unique characteristic of the soil moisture is the beyond its spatial heterogeneity is the memory time scale. And this Professor Manabe and Delver, they have extensively worked using the simple this bucket model during 90s and 80s and 90s. And what they brought out is this soil moisture, they estimated the soil moisture using the decade time scale. And what they showed is the influence of this radiative forcing through evaporation, and what the distinction between the soil moisture memory over the extratropical region and the tropical region. Extratropical region, obviously, it is more than 2 to 3 months, while it is over the tropical region, it is less than or about a month or so. And then in their sensitivity experiment also, what they showed using this the interactive case soil moisture sensitivity experiment, where the control run they did with keeping the soil moisture constant, and then another with the interactive case. And then what they showed is this zonal mean of temperature variation. Again, over this, this is the zonal mean. You can see, of course, in the southern hemisphere, the land region is less, but over the northern hemisphere, in the tropics and subtropical region, the sensitivity it reflects very clearly through this temperature variance. The same way, this our colleague, our student, PhD student, he has estimated this soil moisture memory over the Indian region, particularly over the Indian region, using high resolution MRF model. And this of course, this has been submitted to a journal of hydrology. It is under review. The particular thing what you can see over this thing is the soil moisture memory. The period varies from 10 days, almost more than 10 days to 2 months over the regions of India. particularly over the central region, poor monsoon zone. I will come to this in a minute. This is the actually this Naresh Ganeshi, our PhD student, in his previous following his previous publication in Journal of Hydrology 2020, he had identified this core monsoon zone, core region, hotspot of strong land atmosphere coupling over this north central India. And the same thing he repeated using this high resolution model, and he identified this region where we should be able to focus this. We should be able to see this, the influence of soil moisture with the help of sensitivity experiment. Of course, this how he has computed via Dermer 2011, this coupling strength, how he has estimated here. So this is given here in the detail, but using this sensitivity experiment, where two experiment he has done, we got this dry simulation, where the soil moisture was decreased by 20%, and the wet simulation where the soil moisture was enhanced by 20%, plus 20%. And if you can see these PDFs of extreme temperatures, this is very clearly depict over the north. Of course, this is over the north central India, over this core region where the strong coupling exists. So the temperature extreme increase in this case when in the dry case, and it decreases in the when we reduce the soil moisture temperature. And as I said, this paper is under review in Journal of Hydrology. Of course, again, important thing is the field scale soil moisture observations. That is the main thing actually. And how the field scale soil moisture observation is with the due taking care. There is the area average, and with due care of this heterogeneity. Particularly, why I mean, if we have this information of soil moisture variation at field scale, it will be very useful in understanding extremes as well as the various hydrometeorological applications, such as this frequent floods and droughts, soil erosion, these desertification, then degradation. All these things, I mean, very useful. Of course, this has been well studied in the literature as well as by this climate change report, IPCC report. The main thing is this soil moisture techniques. If you see, there are various soil moisture techniques. I will come to the point that there are point scale soil moisture techniques, gravimetric method, capacitive sensor using the capacitive sensor, TDR, theta probe, etc. But it has the issue also, I mean, limitations also. Gravimetric method, for example, it requires a huge manpower. You cannot have this in frequent time scale. And then the satellite remote sensing, again, it has its advantage and issues. I will more focus here on field scale soil moisture, which is what we are using this cosmic ray soil moisture observation system, which provides the area average soil moisture. What is the area average? This 0.5 kilometer resolution, and it is a high frequency hourly observations. Of course, it will have a lot of usage. And the main thing is, what is this technique? Is this cosmic ray soil moisture sensor? Just, I mean, very briefly, I will tell that this whatever this cosmic ray we receive on the Earth's surface, it reflects when it travels from the atmosphere and reaches the Earth's surface, it loses its energy. And this neutron, I mean, the low energy neutron counts, that is what is captured by this probe. What you see here, just briefly, I am telling, this is a passive method, and I may not be able to explain it in detail, but it captures this neutron count, and these neutron counts are calibrated to soil moisture across the 200-meter diameter region, or say 0.5 by 0.5 kilometer. And this is also having the, I mean, this also gives the this effective depth of this soil moisture deep of penetration. Very small background I will give. This cosmic ray was invented by Victor Hess in 1912. He got Nobel Prize in 1936. And this was earlier, it was this the moisture content in the atmosphere as well as the land surface was considered to be a noise. But in 1966, in 60s, Hendrick and Edge, they brought out that no, it's not a noise, it is a signal for soil moisture or moisture. And particularly, I mean, in the soil, it is a soil moisture signal. And they brought it, that they put it in terms of volumetric water content. percentage of volumetric water content, and then subsequent I'm jumping to this Reda et al. Who had invented this non-invasive probe in 2008. So this technique is the main feature of this is it has the non-invasive probe, and then the desolate how this counts, neutron counts are calibrated. Again, this is the desolate. He came with a desolate curve, and he showed that how it is converted. It is calibrated for the soil moisture. Of course, there are a lot of correction factors. Franz et al. He's a pioneer associated. From University of Nebraska, and he has carried out a lot of calibration corrections in this soil moisture while converting from neutron count to soil moisture. And still it is in the research mode. And of course, again, then the Bogena, I will talk about this, the sensor network. What is the sensor network? How this is calibrated? And the Cosmos network also, again, it is very expensive affair. Of course, it has a lot of this agriculture and other applications. So just coming to the point that this is Cosmos IITM. This observation, this is a part of this Cosmos India network. This has been detailed. You can find the detail in this remote sensing journal. This has been published in 2020. The main thing is, of course, this is a more detail about this location, and it's a geography and vegetation cover. The main thing is, there are various instruments. This is the soil moisture probe, and this is the location, Google location we are showing here. This is the probe, and these are the 60-degree spikes. For calibration, we need to have 108 observations at different depths, starting from 0 to 5. And this is a one sample we are showing the soil moisture profile following Reda et al. 2012. How this is required for the calibration. This is a rigorous method. It requires almost, it consumes a week. And we have to take out this soil moisture profile using gravimetric method. You can see this. These are the error bars or standard deviation, what you say. And the same way we have. This has been done repeatedly. This soil moisture profile for calibration purpose. I will not spend more time on that. And this is a general this characteristics of this soil moisture characteristics over Cosmos IITM. This has been done using the facilities of Agriculture College, Pune. Main thing is the field capacity. You can see this 46% is the field capacity here. And using this all resources, we have published this paper in Journal of Hydrology recently in 2021. I will come to the point that hourly field scale. What is the advantage of this Cosmos soil moisture observation system? That is the field scale soil moisture observation system, or 0.5 by 0.5 kilometer. It gives the soil moisture very high frequency, hourly soil moisture, and with effective depth, the penetration depth. You can see very clearly 2017, 2018, 2019, 2020. Of course, it shows the annual cycle, onset, withdrawal phase, seasonal and subseasonal variations, etc. Very interestingly, I will just come here, 2018. If you see the 2018, 2019, just a contrast here. 2019, as it has been nicely elaborated in previous lectures and plenary sessions, that 2019 extreme events, how it has captured, and what is the influence of this meteorological influence on the soil moisture, how the reflection of this temperature and this precipitation variation on the soil moisture. So this has been very well evaluated using these observations. You can see here again. This I will not be able to describe in detail. Lot of information is there in these two graphs actually. This temperature, daily temperature observations at IITM Cosmos, our site, and the temperature also. So this is actually, if you see the 2018 and 2019, the contrast is 2018 first half was little excess, and the second half was very deficient. And 2019, it started over this region in the June, and it extended up to till beyond October. And you will see the numbers also, very high number. Annual rainfall, it is very, very high over 2019. I'll talk in terms of this. We have tabulated this. Of course, 2020, 2021 also is very interesting. but yet the year has to be over. So we are just when we will be carrying out this in our next paper, this analysis. But you can see this contrasting over this region. I mean, this 2018 and 2019. You can very clearly see that the difference during JJS as well as the annual region also. So the thing is, these are the spells, actually rain spells. So we have just been this rain spell to just show that how the rain spells occurred during 2018 and 2019. The important thing what we want to highlight here is the 2019 had the extreme rain spells and very prominent extreme rainfall spells 2019. You can see very clearly either it is the short rain spells, moderate rain spell 5 to 9 days, or long rain spells 10 days.
Dr. Majumdar?
Yes, sir.
Please, can you summarize first?
Yes, sir. Yes, sir.
How it is hearing time.
Yeah. So this is again this low frequency subseasonal variations are prominent during this thing during 2019. You can see very clearly, and particularly the memory scale, time memory scale. You can see very clearly during 2019 and 2020. Typically, the memory scale is less than, I mean, almost 40 days, but it has exceeded during 2019 and 20 about 2 months. And very clearly, you can see the difference between this realistic representation by Cosmos as compared to GL-DAS or other this thing. And this is just
summarize.
Yes, sir. This is just a network. This is what we are carrying out, and this network we are, of course, what you have seen here is very expensive method. People have done this network and then to get this field scale soil moisture. But here we are doing with the help of these engineering colleges and developing a low cost sensor using the capacity building means. And this is a one profile just to show that up to 1 meter depth. We have done this using the gravimetric method. I will just conclude as I have been told. So this is a quantitative evaluation of this. You have seen this using the Cosmos observations and the comparison we have shown. Main thing is this: all the synoptic, subsynoptic, or these low frequency features are well captured, and the memory time scale also, particularly during 2019. How this 2019 these extremes are well captured by these observations you can see here. And then we have shown also the soil moisture. This is our main attempt to do the soil moisture profiles of 1 meter depth using layer and which shows the layer by layer variability. Future work, of course, we are getting into this field scale soil moisture observation using hydrological models and diagnostic analysis using soil moisture experiments. And main thing is this can be only possible through capacity building, designing, circuit, assembly, deployment, and all these things using involving various faculties and students, expertise, stakeholders from rural area as well as other regions. Thank you very much.
Thank you, Milind Majumdar. So it's a very informative talk. So we are running out of time. So if any question is there, please ask him through chat box, and we'll go to next talk by Dr. Arti Menon from University of Reading, Dynamics and Evolution of Case Study of Monsoon Depression in a High Resolution Model Simulation. Okay. So Milind Majumdar, you can quit the screen and so that she can join.
Yes, sir. Is it okay, sir?
Yeah, fine. Thank you, Majumdar. Yeah, Arti Menon, you can start.
Yeah, thank you, sir.
So you have 10 minutes time.
Yeah. Can you see my presentation?
Yeah.
Well?
Yeah.
Okay, thank you, sir. Good morning, all. I will be talking about the dynamics and evolution of a case study monsoon depression in a high resolution model simulation. Just to give a quick background, the monsoon depressions are synoptic scale cyclonic vortices which usually form over the Bay of Bengal, and they bring substantial amount of rainfall to the central and northern parts of India. In this talk, I will be showing the detailed evolution of a case study monsoon depression of July 2016. Using high resolution model simulations. Why July 2016? That's because as a part of the Encompass project, which was a joint initiative between the UK and the Indian Ministry of Earth Science, we did a field campaign in India. and during summer 2016, and we have the flight observations of this specific monsoon depression. And hence, we were interested to do this specific case study. Coming to the model setup, I used the Met-Office unified model in a nested suite setup for these simulations. The black box in the middle, this shows the limited area model domain, and the limited area model had a resolution of 1.5 kilometers. Firstly, let's have a look at the synoptic conditions during this monsoon depression. So this figure shows the rainfall and winds from 2nd July 2016 to 7th July 2016, which was the period of this specific monsoon depression. And the red stars here represent the center of the monsoon depression on each of these days. So during the initial stage of the depression, we can see that the rainfall is mostly concentrated over the Bay of Bengal, and there is orographically enhanced rainfall over the Burmese mountains. Then we can also see several mesoscale convective systems towards the northwest side of the monsoon depression. That's there during these initial stages on 2nd July and 3rd July. Then on 5th July, the monsoon depression is mature, and we can see that the rainfall is mostly over the southwest quadrant of the depression. And during these later stages from 5th July to 7th July, we can see some rainfall convergence lines towards the west of the depression. And these are frontal rains associated with the interaction of different air masses. I will come to that in a minute. This figure on the left shows the vertical structure of several thermodynamic parameters across this cross-section AB shown in this figure. This is on 5th July, and this cross-section passes through the center of the depression. So if you look at the two left side figures, the top one is for relative humidity and the bottom one shows theta E, which is the equivalent potential temperature. We can see that towards the west of the depression, at around 500 hectopascal, there is this low relative humidity, low theta E layer, and this shows the dry air intrusions approaching the depression from the west. And if you look at the vertical structure of PV, which is shown in this panel D, we can see that there are some filament-like structures in the potential vorticity in the center of the depression. And we can see such structures when we use such high resolution model simulations. And the PV is mostly positive at the center of the depression. So this PV is either generated in the depression from different processes, or it might be advected into the depression from somewhere else. So in this talk, I will be mostly showing the effects of two processes on the monsoon depression. One is the interaction of the mesoscale convective systems, which I showed in one of the previous slides, how they interact with the monsoon depression. And the second one is the interaction of the dry air intrusions with the monsoon depression. Now, going to the first mechanism, the figure on the left shows rainfall and wind for 3rd July, which is during the initial phase of the depression. And the red diamond here shows the center of the depression. And we can see these mesoscale convective systems towards the west. And the figure on the right is the tephigram for one of these MCSs, which is shown by this red star here. And we can see that the entire atmospheric column is close to saturation, and the conditions are favorable for deep convection. So these are the mesoscale convective systems, and we are now checking if they are interacting with this monsoon depression. For that, we did some Lagrangian trajectory analysis. So the figure on the left shows the trajectories on 3rd July. It's a 48 hours forward trajectory starting on 3rd July at 700 hectopascal over this black box shown here, which is a region of the mesoscale convective systems. So we are taking starting the trajectories at 700 hectopascal to remove the artifacts from the boundary layer. Here, the color of these trajectories represent different pressure levels. So we can see that some of the trajectories rise in this region in the upward like deep convection, and then they move towards the Tibetan Plateau region. But majority of these trajectories are traveling south and they are reaching the center of the depression. So these MCSs, so these trajectories could be carrying the high theta E air from these mesoscale convective systems into the depression. So in order to confirm this, we are doing some back trajectories, which is shown in the right side panel. These back trajectories start on 5th July near the center of the depression. What is shown here are 25 trajectories with the highest theta E values. And then we can see that majority of them are tracing back to the region of mesoscale convective systems. So we can conclude that these high theta E air from these mesoscale convective systems are reaching the monsoon depression. They are feeding into the monsoon depression, and this could help in the growth of the depression. Now, coming to the second mechanism, which is the role of dry air intrusions. What is shown here is the vertical structure of theta E and total PV along this cross-section AB shown in this bottom panel. So this crosses through that convergence line in rainfall towards the west of the depression. And so here if we look at the winds, we can see that convergence that is resulting in these frontal rains here. And from the theta E structure, we can see that there is low theta E. There are some low theta E air masses at around 500 hectopascal, which shows the mid-tropospheric dry air intrusions from at around this level. And we can also see low theta E air coming at around 900 hectopascal, which shows some low level dry air intrusions. And when these dry intrusions are approaching this central region, we can see that it is disrupting the vertical PV structure. So these dry air intrusions also must be having an effect on this monsoon depression. To analyze that, we are now looking at the Lagrangian trajectory analysis again. So the figure on the left here shows the 30 hours forward trajectory and 30 hours backward trajectories starting at 500 hectopascal, which shows the mid-tropospheric dry air intrusion. Here the red diamond shows the center of the depression. We can see that these air streams stay at this level around 500 hectopascal. If you look at the color coding, which shows the pressure levels, we can see that they stay at 500 hectopascal for almost 60 hours. And then they interact with the southwestern quadrant of the monsoon depression. So this shows that they are like coherent air streams. And if you look at the right side figure, these are 30 hours forward and backward trajectories starting at 900 hectopascal to look at the dry air intrusions we saw at those lower levels. And we can see that again, these are coherent air streams and they come all the way from over the Arabian Sea, and then they are recurving into the monsoon depression. So these dry air intrusions, the northwesterly dry air intrusions and the westerly dry air intrusions at lower level, they both are interacting with the monsoon depression. So this figure on the right shows actually the time series of these trajectories, which starts at 500 hectopascal. We can see that throughout this time, the specific humidity is quite low for most of these trajectories. And this shows that they are dry air, and the theta E also remains like fairly constant throughout. Like there is not much variation in this. In the
Dr. Menon, can you speed up?
Yeah, I'm almost done. Yeah. So just to conclude, we need such high resolution model simulations if we want to understand the influence of such localized adiabatic processes and airstream advection on the evolution of the depressions. And we found that during the initial stage of the depression, the warm and moist high PV air, high theta E air from the MCSs are reaching the monsoon depression, and which enables the growth of the depression. But during the later stages, these dry intrusions from the Arabian Sea and also from the northwesterly dry intrusion in the mid-troposphere, they interact with the depression, bringing in low PV, low theta E air into the depression, which could hinder the growth of the depression. And we see such similar structures on 7th July, which was the day of the flight observations, and we are planning to compare it with the field campaign observations. Thank you for listening.
Thank
Any
you.
questions?
Thank you, Arti Menon, for a very informative lecture on this high resolution model simulation of low pressure depression. So thank you very much. And we have very less time. So you, what I can say, you can answer the chat box. What are the questions are there? Please, one question is there. You please answer in the chat box. Okay.
Okay,
We'll go
sure.
to the next one. Okay.
Thank you.
Thank you. So we'll go to our next presentation, Dr. Abhijit Day, scientist from IITM Pune. So on real-time performance of extended range prediction system of IITM during Indian summer monsoon season 2021. I now invite Dr. Abhijit Day.
Yes. Are my slides are visible?
Yeah, it's visible. You can make it full screen.
Okay. Yes. Yeah. Good afternoon to everyone. I am here to present the real-time performance of extended range prediction system of IITM during the ISMR 2021. Every ERPS group member has contributed to this work. This year, country as a whole has received around 87 centimeter of rainfall, and that is 1% below normal compared to its normal value, 88 centimeter. So this one I am showing standardized rainfall time series averaged over the core monsoon zone region. So that indicates that during the first half of June, monsoon was somewhat active. That means it is towards normal to above normal side. And from mid-June to mid-July, it was like extended break-like situation was there. And afterwards there was a short active, and subsequently almost whole August was like extended break, and monsoon revived only during September. So I will show the prediction for this transition, active to break and again break to short active, and then again extended break, and subsequently in active condition during September, using IITM extended range prediction system. For this IITM extended range prediction system, we get the atmospheric and oceanic initial condition from NCMRWF and INCOES, and generate the ensemble of initial condition. And 4 ensemble members of CFS Q126 and CFS Q3822 models are run, and SST generated from this coupled model is bias corrected, and that is used for forcing the standalone GFS model. So therefore we have total 16 ensemble member, and simple arithmetic averaging is done to get the multi-model ensemble forecast, means one single forecast from this ensemble forecast. This I am showing the seasonal cycle of rainfall over this monsoon zone region during this JJS 2021. These bars are for observed rainfall, and this black line is model predicted rainfall for week 1 lead, and blue is for week 2 lead, and green is for week 3, and magenta is for week 4 lead. So if you see the seasonal cycle at week 2 and at week 3 leads, the transition, that means the peak and active and break, those are captured well in week 1 and week 2 lead. But in week 3 and week 4, there are some false signal. This I am showing the week-wise verification of rainfall over this monsoon zone region. This pink is observed, and black bars are for model forecasted rainfall averaged over a week, that is written here. And this box is for week 1, right one is for week 2, this is for week 3, and this is for week 4. And these are the model forecasted bar. And if you notice that at week 1 and week 2 lead, that active to break and this extended break during August, and then transition means then from break to active in September was well captured in week 1, week 2 lead, and that was reasonably captured in week 3 and week 4 lead. And this blue, green, and red, these are the probabilities of above normal, near normal, and below normal categories. Means we have total 16 ensemble members. So how many ensemble are showing rainfall probability in a particular category? That has been shown with this bar. This I am showing the week-wise scale of rainfall over different homogeneous region. This is for 4-week lead: week 1, week 2, week 3, and week 4. For black is for all India, red is for monsoon zone region, green is for central India region, blue is for northeast India, and yellow is for northwest India, and this gray color is for southern peninsula region. So if you notice that during week 1 and week 2, most of the region, particularly this monsoon zone and central India region, up to even up to week 3 lead, we have good skill. But at week 4 on over this northeast India and northwest India, the skill drops drastically, and it shows negative correlation. This is the meteorological subdivision-wise skill. This left panel is Hincus skill during 2003 to 2019. During that, using that period data, and the right panel is using 2021 JJS data. That indicates that this year we have we had good subdivision, meteorological subdivision-wise skill for over this region, over most part of the northwest India and this Jammu Kashmir region. And even in week 2 also we had good skill over most of the subdivision, except few subdivision over central India region. But that subdivision wise skill also that skill drops drastically in week 3 and week 4 lead. So it is skillful up to week 2. This I am showing the subdivision wise categorical deterministic and probabilistic forecast of rainfall based on 1st September initial condition. We have there was demand from different sectors that they want subdivision wise forecast. Although we don't have very good skill over many subdivision, even up at week 2 lead also, but still due to huge demand, we have started analyzing and started giving the product of net subdivision wise data of different meteorological subdivision.
This today you have 1 minute left. You have 1 minute. You can speed up.
Okay. This left is for deterministic, and this right one is for probabilistic. So in probabilistic, we have from different category: below normal, near normal, and above normal rainfall category. And this one is based on ensemble mean values. So percentage anomalies has been calculated for each subdivision. And in the right panel, we have 16 ensemble members for every subdivision, and based on that, how many members are showing rainfall probability in a particular rainfall category in that above normal, near normal, or below normal category, and based on that, probability has been calculated. I will show the verification of few break spell during the first half of July. That we have seen that during first half of July it was break. That this is observation, during 1st to 7th July, and the lower panel is for model forecast based on week 1 lead, week 2 lead, week 3 lead for the target week 1st to 7th July. And that model also indicates the break light condition over this week, and similarly subsequent week also. And another break spell during the August also, that was also well predicted up to 2 to 3 weeks in advance. And the revival of monsoon during the September, that means we have seen that during from 9th September onwards, rainfall started reviving. So that our model also predicted up to 3 weeks in lead that revival of monsoon. So active spell during this September was also well forecasted with reasonable lead time.
Dr. Day, please
This is the
conclude it.
offer.
Please,
Yes,
please
yes.
conclude. And you have already.
Yeah, so I'll come to the conclusion slides that MME could realistically provide an outlook on interseasonal fluctuation, and over most of the homogeneous region of India, MME shows a useful ski up to week 2 lead, and MME could predict the large-scale enhanced and surface phase of the convection associated with large-scale meso. Thank you.
Thank you, Dr. Day,
Your
for
attention.
presenting a very informative talk on the performance of IATM model during the summer monsoon season of 2021. Thank you. So now we'll go to the next talk by Dr. Srikala PP from KUSAT. Okay. Srikala?
Yeah. Am I audible?
Yeah, you are audible. You can start.
My presentation is visible?
Yeah, visible. You can make it full screen.
Yeah, I made it. Is that okay?
Yeah, you can start.
Okay, good afternoon, everyone. I'll be presenting the topic on the simulation of northeast monsoon rainfall over southern peninsular India in CIMIC 5 models. So we know the northeast monsoon is most important for the southern peninsular India, especially for Tamil Nadu, because Tamil Nadu is a rain shadow region during southwest monsoon. So it depends on northeast monsoon for various agricultural and hydrological purposes. As you know, there is 17 to 49% of the annual rainfall is for Tamil Nadu is from northeast monsoon rainfall. So this is this figure shows the large scale rainfall pattern. As you can see, the maximum rainfall is over the maritime continents, and OLR, that is the measure of convection, is also shown here. Below normal OLR is found over the maritime continent, and these two OLR and rainfall is matching very well. And the coefficient of variation of northeast monsoon rainfall is very high. Or the South Peninsular India, it is around 25%. And so it is difficult to predict the northeast monsoon rainfall. So this just I want to show the trend in northeast monsoon rainfall. We have seen a positive trend over Indian Ocean as well as over the southern peninsular India. So it is important to study how the rainfall is going to change in the future. CIMIC 5 models provide substantial experiment outputs which can be used for studying the climate variability as well as the future projection. And we have seen various previous studies reveal that the interannual variability of northeast monsoon is positively correlated with the El Nino Southern Oscillation and Indian Ocean Dipole. Actually, southwest monsoon rainfall is negatively correlated with El Nino, but it is not the case with the northeast monsoon rainfall. And the previous studies also shows that there is a poor scale in simulating the mean state and interannual variability of northeast monsoon. So here I checked whether the CIMIC 5 models are able to get the mean and interannual variability of northeast monsoon rainfall over southern peninsular India. And I have used 34 simplified models. The model is shown, the selected models are shown here. And other data sets I used for the study includes the SST, harder SST, and monthly data sets for zonal, meridional, and vertical wind from ERA 5 reanalysis data, and GPCP rainfall. So coming to my result, this is the mean northeast monsoon rainfall simulated by CME5 models. As you can see, this is the observation and the actual data by using GPCP rainfall from 1979 to 2005. And this is the multi-model ensemble. Even though it shows a reasonably well pattern, there is a excess rainfall over the Western Indian Ocean. The pattern correlation and normalized ST is given in this Taylor diagram. As you can see, the pattern correlation ranges from 0.6 to 0.9. And we calculated ratio, that is the ratio between the pattern correlation to RMSE. It gives the how well the model is predicting the mean rainfall. So based on this ratio, we have selected 5 low skill model. LSM stands for low skill model, and 5 HSM high skill models. So I have analyzed this LSM and HSM for further analysis. So this shows the multimodal ensemble bias and HSM bias and LSM bias. As you can see, the bias in rainfall, this is for rainfall, bias in rainfall is very high over West Indian Ocean, Southwest Indian Ocean, and there is a negative bias over the southern peninsular India. And we have analyzed the wind. There is an equatorial westerlies during the northeast monsoon season, and so it is here you can see the equatorial westerlies, and these equatorial westerlies are simulated comparatively well by HSM, but these equatorial westerlies are absent in low scale model ensemble, and we can see there is a convergence over the Southwest Indian Ocean. So I have analyzed the SST pattern. So here we found that there is a positive SST bias over the Western Indian Ocean, and it leads to the excess ascending motion over the Southwestern Indian Ocean. It is evident from the water circulation, and this leads to the excess rainfall over the Southwest Indian Ocean. So now coming to interannual variability of northeast monsoon rainfall. As I said earlier, the El Nino Southern Oscillation is positively correlated with the northeast monsoon rainfall. This is the composite of NMR rainfall during El Nino, La Nina, IOD, and negative IOD. Here we can see Western Indian Ocean rainfall over Western Indian Ocean is positive during El Nino and IOD, and Eastern Indian Ocean and Arabian Sea is less during El Nino and IOD. Just opposite kind of anomalies found for La Nina and negative IOD. And the probability analysis also shows that El Nino and IOD shows the probability for excess rainfall, and its combined effect shows a 0.63 63% probable for an excess rainfall. So we checked whether this correlation is simulated by these 34 models. And as you can see, around 70% of models were not able to get the positive correlation exists between the Southern Peninsula Indian rainfall and 3.4 SST, as well as the Southern Peninsula Indian rainfall and DMI. So we selected, here we selected the models which shows the positive correlation, and few models, 6 models actually, from which actually shows a good skill in simulating mean northeast monsoon rainfall. So
speed up, please.
Okay.
Time is in your time. You are just speed up.
Yeah. So these are the models I selected. So this is the regression maps of NINO 3.4 SST onto northeast monsoon rainfall and SST and wind. This shaded portion is SST and contour. Blue contour is for rainfall and wind. So here we found that this Pacific cold and the warm anomalies over the Pacific cold tank is extended more westward in the low skill models compared to the high skill models. In the observation, it is only up to 160, but in low skill models, it is extended more westward. This kind of pattern we have seen in IOD regression as well. So we have checked the Hadley circulation. It is due to the presence of called SST anomaly. We have seen a descending motion over 10 degrees south to equatorial region to 10 degrees south in HSM, but still we get ascending motion over the 5 to 10 degree north region. This is comparable with the observation, but we can see the descending motion over the southern peninsular Indian region in the low scale model, which leads to the negative correlation. This can be found in the yeah, it's all.
Please conclude, please.
Okay, this can be seen in the DMI case also. I have checked the Walker circulation as well. Here also we found the ascending motion over the southern peninsular India, which is well simulated by HSM, but not by the LSM. The similar pattern found in DMI. So the summary and conclusion: Simify models simulated reasonably well with the pattern correlation ranges 0.6 to 0.9. A positive IOD like mean SST bias in Indian Ocean and weak land in a like mean SST or Pacific Ocean is observed in low skill models, and the low skill models could not simulate the observed equatorial westerlies, which leads to the ascending motion and unrealistic wet bias over the Western Indian Ocean and dry bias over the southern peninsular India, Southeast Asia, and Southeast Indian Ocean. And around 70% of Simify models were not able to capture the observed positive correlation that exists between this southern peninsular Indian rainfall and 3.4 SST as well as with DMI, and Lino and POD related warm SST anomalies over the equatorial Pacific cold is found to be extended more westward. This leads to the descending anomalies over the northwestern Indian Ocean and southern peninsula, which causes the erroneous dry anomalies and which leads to the erroneous negative CC exist in the Simify models.
Thank you.
Thank you.
Thank you, Srikala. We are already late by 15 minutes, so we are not taking any questions now. If anything is there in the chat box, you please answer that. And
Okay,
in this session, we had a very interesting talks, nearly 7 talks on seasonal prediction by IMD and the Indo-Gangetic Plain, the climate changes over the Indo-Gangetic Plain, and the deep convection understanding, and soil moisture variations, and high resolution simulation of monsoon depression, and extended range monsoon prediction by IATM, and the last talk on northeast monsoon rainfall simulation by CMIP5 models. So it's all interesting, and thank you for all the speakers, and I thank the organizers for providing a chance to chair the session along with Dr. G. Srinivasan. So thank you. Back to the organizers. Thank you.
Thank you, sir. And we thank Dr. G. Srinivasan and Dr. V. Satyamurthy for your valuable time and effective management of this session. We also thank the speakers and audience who have attended online and offline. And the next section, the Periyar Hall, will begin at 2:10 p.m. Thank you.
Thank you, Ajay.
Hello.
Good afternoon.
Good afternoon, sir. Good afternoon.
Hello, Ajil. How are
Hello,
you?
sir. Hello, sir. Fine. Good afternoon. Yeah. So, sir, actually, the session will start at 2:50 p.m.
2:15 or 2:10?
2:10.
2:50. 2:50.
It means first speaker will start speaking at 2:15.
Ah, okay.
Session we can start. 2:10. Sorry.
Rajan sir, good afternoon.
Hello, Anand.
Hello, sir.
Hello.
Good afternoon,
Rajan
sir.
sir. How are you?
Long time I am seeing you.
Long time, sir. Maybe at least 10 years we haven't met.
Yes. So I was just telling Pawan Kumar and others, our staying in your house in US.
Yeah. That's long back.
Wonderful time.
Yeah.
How is Pune, Anand?
We are missing you, sir, here. No, we don't have the habit of calling you over phone, only meeting you once a month. But that didn't happen last 2 years. Yeah.
So you are now in university, Pune University, isn't it?
Yes, sir.
There, Sen is there, I think.
Yeah, Sensor, yeah, he is a visiting faculty. He comes he used to come regularly, but last 1.5 years, yeah, once in a while he comes.
Yeah.
Professor Sen was the chairperson in day first.
Yeah, he was here yesterday. He came here yesterday.
I have been to university, Pune University, for 2 PhD vivas.
Okay, yeah.
Long time back.
I think after I joined, you came once.
Once.
Yeah, once, yeah.
Good afternoon, Rajan sir.
Good
So you are my PhD examiner in IIT Delhi 2004.
Yeah. So I am extremely happy to see people like you.
Yes, yes. So after a long time, I met you this forum.
Yes. So I am so happy. IIT Delhi's life, and that time I used to be there at least 6 months in a year.
Yes.
Yeah. And I used to stay in the guest house.
Yes.
That's all sweet memories.
Yes.
Where are you now working?
I am in MIT University, Jaipur, sir.
Jaipur.
Yes.
There we are having the atmospheric science or.
Yes, sir. Professor Dubey, when Professor Dubey was Vice Chancellor here, he started the Center for Ocean Atmospheric Science and Technology, MIT Coast. So the center is since last 5-6 years it is going now.
Good. You are now in charge of center, or?
Yes, sir. I am the director of the center.
Very good.
So we have PhD program we are running here.
Good.
So, though it is a very small center, we have only 2 faculties right now working in the atmospheric science, and 2 are environmental science.
Then others are coming as guests.
Yes.
I think that is the workable solution.
Correct, sir. Yeah.
Anyway.
Good afternoon, everyone.
Namaskar, master.
Good afternoon, Professor Ashok.
Good afternoon, Professor Anand, and namaste, Professor Rajan. Hi, Professor Subraj. Hello. Yeah.
How are you?
I'm fine. I'm fine. Thank you. How are you?
I am quite fine.
Very good, sir.
Only one thing, the frequent movements has stopped.
I see. I see. Okay.
You are working where?
I'm faculty in University of Hyderabad.
University of
Hyderabad.
Hyderabad.
Hello, Professor Mohan Kumar. Good to see you again.
Yeah.
How are you, sir?
Yeah, fine. Yeah, we are busy with all the programs.
Yeah, I can understand. Yeah. Nice to see Anand also. All of you.
Yeah, after quite some time, yes.
Quite some time. COVID has made us all, islands.
So we have got 3 parallel sessions, parallel hall at the halls.
Okay.
Yeah.
It's going very well, I think.
Okay.
Lectures and then.
Okay.
Most of them are available in YouTube also.
Yes. I shared it with all my colleagues and students and I hope I'm in the right place, right? With so many things.
Yes, don't worry, you are at the right place.
Okay.
Okay, I think we will start at 2:10.
2:10. Yeah. 2:10. Shall I just quickly check my?
Yeah, please check it.
Yeah,
Verify your.
it's better to.
Yeah, whether it is moving or not also check.
Yeah. Should I have to leave the meeting? Why is it giving leave the meeting and join? Okay.
Oh, sorry, you are still at the meeting.
Ajil, are you asking us to give the name here or?
No. I was. For delegates, those who have joined as delegates, just add their names so that we can promote them to panelists.
Okay, sir. Those who joined here as delegates, please add their name so that we can see the list and confirm that that particular person is present here.
Some are attendees. Yeah. To promote them as a panelist, we need their name.
Okay. So to promote them as panelists, we need names. So those who joined here, please give your names.
Can you write in a chat box?
No, sir. In the attendees list, you can just type your name instead of just giving the name of institute. But for your case, it's okay, sir.
Okay.
Please give your name. But we see that there is one name called IATM, but we don't know who that person is. So
can you see my screen?
Not yet. Yeah, it has come. Yes.
Okay. Thanks a lot. Okay. As and when you suggest me to start, I will.
Yeah, I think we have
still more time.
5 more. Are we starting at 2:10 or 15?
2:10, sir.
2:10. So 4 minutes more.
Yeah.
So Rajan sir, how we are doing it? First, splitting.
Yeah, see, fortunately, by God's grace, I am fine. Even now, I am keeping touch with the subject.
Okay, very good.
Yeah, and writing some of the articles connected with the heavy rainfall of Kerala.
Okay, sir.
2018 onwards. So that then going to the channels as per their request, giving what all help society needs.
Okay.
So that way I am keeping
active.
Quite active.
Yes, very good.
Let's see how long I can do that.
So very few participants because most of them are on YouTube or only 12 or.
Yeah, I think mostly.
Yes, are only speakers and chairs.
Yeah.
Okay.
Others can watch from website and the YouTube. This Zoom link is provided only to the speakers and the delegates.
I see. Anyway, I have sent my presentation to Anand also, just in case of any issue.
Yes, sir.
Okay.
So we can see your presentation and.
Yeah. Just in case, I already not Anand.
Yeah, you can stop.
Abhilash, I sent the presentation to Abhilash in the morning. In case of anything, any issues that it can be downloaded.
I think let us start our session. And welcome to session on monsoon, seasonal variability, prediction and predictability. And this session is being chaired by Professor C.K. Rajan and Dr. Anand Kumar. Dr. C.K. Rajan is a former professor and head at Department of Atmospheric Sciences, CUSAT. He is well-known meteorologist and has been instrumental in setting up in-situ observation across Kerala. Dr. Anand Kumar Karipot is a professor and head of the Department of Advanced Sciences, Atmospheric and Space Science at Pune University. He specializes in atmospheric sciences and has done works on carbon flux measurement and evapotranspiration. So in this session, we have two lead speakers, Professor K. Ashok from University of Hyderabad and Dr. P.V.S. Raju from Amity University. Professor Ashok is from Center for Earth, Ocean and Atmospheric Sciences, University of Hyderabad, and specializes in climate modeling and in monsoon variability and extreme events. Dr. P.V.S. Raju is the Director, Atmospheric Sciences and Climate Management, Amity Center for Atmospheric and Science Technology. So we have two invited talks, Dr. Prashant Pillai from Indian Institute of Tropical Meteorology, Pune, and Professor Toru Tirayo from Kagawa University, Japan. After the invited talks, we'll have 3 oral presentations in this session. For the timely conduct of our session, we have prescribed duration of our talks and presentation. The lead time is for 20 minutes. The lead talk is for 20 minutes plus 5-minute discussion. Invited talk is for 30 minutes presentation plus 2 minutes discussion. And short oral presentation is for 9 minutes plus 1 minute discussion. We request the speakers to adhere to the allotted times. The selected question in the chat box will be conveyed to the chairs by the rapporteurs. Now, may I request honorable chairs to kindly take over the session.
Okay, thank you very much. Let us, Dr. P.V.S. Raju from Amity University, Jaipur, may please.
Excuse me, I thought I was the first person. I have a meeting also actually later.
Okay, Ashok. Okay. Then
guys, Professor Ashok first.
Okay.
As per the list.
Dr. A. Ashok.
Thank
you. Hyderabad, isn't it?
Yes.
You may.
Yes, sir.
Please.
Yeah, thank you. So
the topic is decadal prediction of the Indian Ocean dipole.
Yes. Good afternoon, everyone. At the outset, I thank the organizers for having given this opportunity to me to talk this, give a presentation. And the title is Decadal Prediction of the Indian Ocean Dipole. This is part of the thesis of my student Periyar Francis, who incidentally has submitted her thesis today. And it has appeared in Frontiers Climate a couple of months back. So flow of the talk is introduction and basic background, various temporal scales of prediction and data sets, and what is this decadal prediction and our results basically, and potential mechanism, summary, limitations and scope, and acknowledgements. Well, the session is on monsoon predictability, but monsoon skills, it's not only when you say monsoon, it's not only the monsoon, its drivers are also quite important. So we know that since, almost more than 150 years, we know since Walker's time, the ENSO has been known to be the impact, that the association with ENSO and the impacts are well known now. ENSO is the biggest driver of the Indian summer monsoon. However, in 1999, the Indian Ocean Dipole was discovered. This is an interannual coupled ocean atmosphere phenomenon in the tropical Indian Ocean, and it peaks during boreal fall, but many years, the signal, it starts in April, and by the time of June, July, August, the signal is significant enough. Positive IOD and positive IOD events, if you see the right picture, are associated with the cold SST off the coast of Indonesia and flanked by warm SSTs to the west. And this is associated with changed water circulation. And you can see in the bottom, the your thermocline is shovels in the East Indian Ocean, and there is coupled dynamics in this one. So IOD has a significant coupled ocean dynamics, and it's always there has been always an argument that IOD was nothing but part of an El Nino, but later on, since then, a lot of papers have come out and demonstrated that individual IODs do exist. Majority of the variability comes from local coupled ocean dynamics. Of course, ENSO and IOD trigger each other, as have been shown in several papers recently. And one of this slide from one of my old papers tells you that the Indian Ocean Dipole Mode Index, the index is actually SST averaged over anomalous SST averaged over western box minus eastern box. That is very tightly coupled with the equatorial zonal wind. So if you do the wavelet coherence, there is a very, very strong significant coherence between this equatorial winds and Indian Ocean Dipole Mode Index in 1960s and 1990s. This paper was an old paper, so the analysis pertains to only that. But during 1980s, the equatorial winds were more strongly connected to El Nino when there was no signal with IOD. Incidentally, this is the period when there is no IOD event was there. What I'm trying to say is that the coupled dynamics of Indian Ocean Dipole are not necessarily always related with your ENSO variability. But strong ENSOs and strong IODs, such as in 1997, they can connect through atmospheric bridge, and interconnectivity is there. They can amplify the modulation and are triggering. They can ENSOs can act as trigger of Indian Ocean Dipole and vice versa, as shown by Izumo. The important thing is the Indian Ocean Dipole events also have a global teleconnections, as this is a slide from our textbook chapter. The pictures were generously contributed by Dr. D. Srinivas and CMRWF. You can see the global connections, over the summer monsoon, positive IOD events cause more rainfall over India, and deficit rainfall in the winter rainfall in Australia, and all over of course, it's the very first paper, Sajid et al. Demonstrates the excess rainfall over Africa. Then Preeti in IITM has done some work, and deficit rainfall over Indonesia. You can see the Americas also. There has been a lot of work on this one, and the peak season of IOD is SO, and you can see similar signatures here. Now, slightly moving off the radar to direction, going back to the basics. We know nowcasting is a few hours of forecast weather prediction, and medium range weather forecast is a few up to 5 to 7 days. Then extended range prediction up to 3 weeks. That's what we are doing now. And seasonal prediction, one season or 2 seasons, even more. Then comes decadal prediction, then climate change predictions. If you see the top 3, nowcasting, weather prediction, and medium range weather forecast, they're essentially initial atmospheric value problems. Even the extended range prediction is also somewhat similar, but you can the SSTs may play a role there. And seasonal prediction, it's a major LBC, lower boundary condition driven one, but definitely initial conditions do play a little role there. But definitely it's a seasonal prediction. From then it will be majorly LBC driven one. That's the basis of the seasonal prediction, as those who are familiar with KNGV works know. Then comes your decadal prediction. Interestingly, it's of course LBC, and there are some arguments that is initial value problem, but I will explain about it later. Then comes your climate change projections. Anyway, anthropogenic and all, this is totally external and internal, both the variabilities are important. External forcings like greenhouse gases, etc. Okay, this slide is from Dr. Juni Lee. So you can see it is a very nice seamless weather prediction problem summary. You can see that, among what are the factors that are important for different scales of prediction. And if you see the decadal prediction, there is this PDO and AMO, these sort of things are there. And so these are the, of course, SST is the lower boundary condition. Subsurface waters are important, temperatures are very important. But along with that, your vegetation, and what I would like to draw your attention is to atmospheric chemistry also. So when we say initial condition dependent, this is mainly just as, you know, with the industrialization, there is an argument, if I'm correct, by people like Eric Goliardi, that aerosols and, you know, the greenhouse gases, the trajectory are almost, you know, they're very well, they constrain the weather. We know a lot of work starting with Gablov and Suvarna Fadnavis and many others who talk of the impact of aerosols on monsoon through modeling also. This is an important aspect that probably constrains your trajectory decadal prediction and gives you a hypothesis that decadal variability is predictable. Okay, so but the science of it and technology of it is, though this claim is intermediate, still I would say nascent. There's still a lot of argument about it. Okay, so so this is an emerging discipline under climate prediction for the near future, 5 to 20 years. This is the time when you give a forecast, you will see that it's not after 100 years, whether it comes correct or not, will be there. So decadal prediction has to resolve initial weather problems, as in weather prediction. That's what from this Mills paper, but I would argue it's more for aerosols and all, more related to that. Then it's not your winds and etc. etc. Of course, in a sense, ultimately it has to evolve continuously. Then your slow varying oceanic process, snow cover, etc. Of course, your global warming trend also gives you a predictability there. So as you go towards decades, it becomes a forced boundary value problem from an initial value problem. Okay, so then intra-annual prediction skills, we know that El Nino has an excellent, all the models now, have come to a stage you can, there are very good prediction skills, even up to 1 year. And so skills, you can see, these are some of our old results, but up to 4 to 6 months, and even DJF season, the peak, you get a, even at 6 month lead, you get a skill of 0.9. Whereas coming to El Nino Modoki, the other type of El Nino, the skills are still there. DJF, you get a skill of 0.7. Fine. Still, with all that, somehow we are unable to, we failed to predict the demise of El Nino in 2012 and the patterns in 2014. That's the information for some other talk. And coming to Indian Ocean Dipole, it's totally a different ball game. Skills are very, very poor. If you take the peak period of SON, the lead skill can at best go to, this is an MME skill, 0.7. And if you take for JJA, when the event is mature, developing, and it's important for summer monsoon, you can get a skill to 1 to 1 month, 3 month lead, but 4 to 6 months, it's very poor by many models. One of the best models that predicts your Indian Ocean Dipole index is Luo's syntax F model of Jamstack. And even that, people take the East Indian Ocean box because it's supposed to give you better prediction there for various reasons. Even here, I'm not going to talk about the full slide, but the lead skills are at up to 1 year. 1 year. Some of the good years, you get a skill of up to 1 year and maybe a little more. Okay, but this is one of the best models. Then the decadal prediction skills are very, very strong in the mid latitudes and particularly North Atlantic, as can be seen from the very first paper by Doug Smith from UK Met Office. There have been several papers which talk of the decadal prediction in North Atlantic, as this slide shows you from Mueller et al. But mind you, this is the skill has been averaged over 2 to 5 years, whereas we do it probably for the first time we are doing, anybody's doing that, we take the skills from each year, 2, 3, 4, 5, 7, 8, 9, 10. Okay, so these skills, you can see a strong decadal skill, significant skill in your mid latitudes. Interestingly, you get some skill in Indian Ocean also, but tellingly there is no skill, very strangely, no skill in Pacific. Then where is the skill coming from? The SST skill, if you see that in the bottom panels, lead 1, lead 2, lead 3 to 5 average, and 7 to 9, the skill is, it's there up to 3 to 5 years, but it's weakening slowly beyond that. What our skill is there is coming basically because of the upper ocean heat content, upper 700 meters. So this is the Atlantic skills. Okay. So far, many people have tried to look at it. There was not much skill in your tropics. Okay. When I say tropics, I'm talking of ENSO. Will not even think of monsoon at that time scale. Then we downloaded the CMIP5 data that are available that have been available to us. So these 4 models were downloaded. Actually, FEBA analyzed the Hadley Center deck press also. There was not much skill there, so we're not showing it. And these are all part of this CMIP5 and validation with HAD assist and OR assist. So what do you, and this one, if you see, this is the details of the model. Actually, I think I have accidentally hidden one slide. If you see the initialization, these 2 red models are the better performing models, as you will see. One of them is full initialization and another is only anomaly initialization. It doesn't seem to affect much, at least within this sample of models, but you never know. If you have a more set of models like CMIP6, that will it will be very much easier to, interesting to check that. So the ensemble mean of 10 initialization of the model outputs have been calculated, and we divide them into different leads. Each run has this CMIP5 run is last 51 years. And so you have 10 initializations. Okay. So we take the ensemble mean and we do the predictions for IOD, ENSO, and ISM for the record. And EOF is just sort of a supplementary result verification. So if you see the skill, for example, this 1960, starting with 1961, 10 ensembles were run up to 2012, 51 years. Similarly, each model in this CMIP5 decadal runs for 51 years at each year, 61, 62, 63, up to 70, you can see. So now if you see all these pink ones, the 61 is the year 1. Here 61 initial condition, 62 is the year 1. So all these ones are year 1 lead. Similarly, these blue colors are all year 2 and green are all year 3 lead. So this gives us a wealth of data from various models at different leads. Okay, I hope I gave you the methodology quickly. Now, ENSO prediction, we start, this first one is actually 1 year lead, actually, not 0. And up to 1 year, the skills are quite good, above this threshold of statistical significance. And up to 2 years, you can get the skills, but they're all coming down. Same thing was published by Gonzalez et al. With more number of models. And again, same thing. After 2 years, there is no model skill for El Nino, no predictive skill. So now FEBA's results, if you see these models, we see that the bottom 2 don't have much skill here after one year. But interestingly, GFDL and CAN-CM4 have skills maintaining up to almost 10 years. Of course, you can see that CAN-CM4 has fallen below the 95% confidence level, this dashed line, for a couple of years, but actually it's above 90% confidence level. We're talking a year 3 to 5. So this gives us a very nice opportunity to at least, whether it's really translates into prediction or not, we don't know, but there is a predictive skill. We'll see. So we also ascertained that this skill is also robust to persistence. If you persist the first year value, whatever you predicted, whether your prediction is more than that. This is a standard technique, as all of you seasonal prediction folks know. And just as a verification, these 2 models, this is the HAD ASST EOF2, which represents Indian Ocean Dipole, and same thing in ERA interim. MEROC and CAN-CM4 also reproduce this pattern. The CAN-CM4 dipole pattern is slightly what you call as a bit funny, but still you can see the dipolar signal. And this GFDL also shows a dipole, but that's more into southern hemisphere. So it's not definitely tropical dipole. In real terms, there are the green circles. If you plot the Indian Ocean dipole, the line shows you the Indian Ocean dipole. The green circles tell you when both models have simulated the observed phase. And red dot tells you that one model has been successful in capturing the phase of the event that occurred. These are all past IOD events. So yes, there are few cases that have been similar. For example, 97 Actually, it should have been red. One model has predicted, and several green. These IODs have been predicted, and negative IODs have been predicted at different leads: 7 years, 5 years, 3 years, and 1 year. These are the lead prediction skills. Very interestingly, you see that there are decades when negative IOD predictability was better, whereas here positive IOD events have been predicted. Phase. I'm talking of phase. I'm not talking of magnitude. We're not there yet. So way back, we talked of decadal IOD patterns, a slow moving, similar to IOD, but a decadal IOD, analogous to one Manabe-Simpson's decadal ENSO. Maybe that background decadal IOD, is it decadal IOD or really signal that's coming from somewhere else, intraannual signal? We'll see. We checked this pattern. We took the subsurface heat content, 300 meters to 800 meter depth ocean subsurface heat content, and correlated with Indian Ocean dipole. But this heat content lags the IOD. For example, this is 10 years before the IOD. If you take the lag correlations with this heat content, before 10 years, you see this warm SSTs in this part in south of Africa. Then the signal is moving east. You can see by 8 years and 7 years and 6 years, this skill is there in this part. Importantly, from 6 years, what happens is from here, understand that there are currents that move towards north. So we took that path. That is a path for tropical area, the signal to come to tropics. So when we do that at 6 years, we see that from the correlations, the signal is upwelling into mixed layer. Then by the year 4, the signal propagates and reaches equatorial area. Okay, into south, north of 10 degrees south. From here, it's a bit strange that the signal is there in the equatorial area, but it's not coming out for the next 3 years, 2 years, and only in the IOD year it comes out. This means that the signal from Southern Ocean is here, but it needs a trigger. It needs a trigger for the signal to, a signal to come out. So it's a coupled phenomena, and we know that monsoon winds can change and trigger the wind, Saji's paper, and some strong ENSOs or anything. You need a trigger to pull this water. Basically, the Southern Ocean is sort of signal is what you call is conditioning the Indian Ocean dipole signal. There is this mechanism. There are several papers that talk how the waters from Antarctic can come to Indian Ocean. Several papers are there. So for whatever it's worth, the model correlations also represent somewhat qualitatively at 10 years before you see the signals in the both models in the Southern Ocean region. So the mechanism, basically deep waters, 300 to 800 meters before 10 to 8 years start, and they come upwell along Somali coast and come here, and the weight to be pulled up. So basically that's the summary. 2 models are capable in predicting the IOD years as lead years, year by year. We have seen that. And yes, from Southern Ocean, they come into the equatorial Indian Ocean. Interestingly, none of the models have predictability in ENSO beyond 1 year lead. We have also seen the other Atlantic paper there. Only today I realized that they too don't get that. Why? Whereas it's supposed to be it's the best predicted skills for ENSO on intraannual time scales. There's a lot of gaps. There are a lot of gaps. And we had just talking of phase here, but with new models, new technologies, more data initialization, I'm sure we'll get better skills. And this gives us a handle. So despite the gaps, it's a tantalizing opportunity to look at it. And maybe what we have done is purely random. I mean, results are fluke, but we don't know. But I believe there is skill there and more. We have to explore that. And if you can predict the Indian Ocean dipole well, at least the phase or sense of it, it will be very useful for policymakers. Thank you. And I thank the organizers once again, and for all the audience for attention. I'm ready to take any questions.
Thank you, Professor Ashok.
Thank you.
Are there any questions on the chat box?
Chat box, okay.
I don't see any questions for Ashok.
Okay. So it's done.
No. I have got a question.
Yeah, please.
that is Indian Ocean dipole and its decadal predictability, etc. you have given. Yes, fine. But in the recent years, the whole monsoon activity and the activity in the Indian Ocean near the equator and north of the equator, that is having a tremendous change, and you are not getting the actual monsoon activities connected with the INSO or dipole.
Okay. Okay, can I answer that question?
Yeah. Hello?
Yeah, can I answer the question?
Please.
Your comment is that of late the Indian Ocean dipole and ENSO are not affecting the Indian summer monsoon.
Yeah.
I beg to differ with you on that. There have been a lot of studies that talked of ENSO weakening, starting with Krishna Kumar. In fact, the Indian Ocean dipole impact, we showed that the apparent weakening was because of the Indian Ocean dipole during 1997 and all. So ENSO impact has never weakened. Its variability. For example, ENSO Modoki 2014, people thought it's a La Nina, but no, it's a Modoki and its impact is very strong. 2009 basin-wide warming, it was very much there. And 2015 El Nino is, we know all the droughts that happened. And 2019 Indian Ocean dipole. After, there was also 2005, 6, 7, 8 positive dipole events with affected monsoon, positive rain. And 2019 is mother of all El Nino, all IODs. And it resulted in heavy rainfall over India. And 2015 ENSO was associated with a lot of droughts over India. So I don't think the impact has weakened. Definitely when a global warming signal is there or decadal variability signals, the opposite, there will be always a competition. That's what when there is a strong IOD, it will reduce the ENSO effect. It doesn't mean that ENSO signal impact has weakened. As long as ENSOs are strong or IOD is strong, their impact is always there. We have shown this in our paleo model analysis also. On long-term centennial changes can also modulate ENSO-IOD relation.
Okay, thank you.
Okay. Okay, then. Thank you very much.
Also, just one general question regarding IOD.
Yeah.
So IOD matured phase occurs during September to November.
Normally.
So the influence of that is seen in Northeast monsoon in your studies or somebody else?
Actually, papers by Pankaj Kumar and Kriplani have done that already. Okay. They have done a lot of work on that. Actually, the signal is much more prominent there. So you remember Pankaj Kumar, he's in Isaac Gopal now, and Kriplani and Roop Kumar, they have all done some work in that. In fact, the signal is much more prominent on Northeast monsoon as compared to summer monsoon, I guess. Okay. Yeah.
Okay, thank you, Professor.
Thank you then. Thank you for the opportunity. Bye. Yes. See you.
Next speaker, Dr. PVS Raju.
Yes, sir. I'm uploading my talk.
Please.
I couldn't find my.
Any problem?
Sir, you can share your screen. There is one green. So should
1 minute, just.
Yeah.
Yeah, now it is coming. Yes. Thank you. Can you see my slide?
Not yet. It's yeah. Now yes.
Yeah. Very good afternoon. Thank you, Chairman. At the outset, I would like to thank organizers for inviting me to this talk. So today I'm going to talk on Indian summer monsoon simulations in regional climate model, performance of parametrization scheme. It is my student, PhD student, is working on this regional climate modeling. He is Mishif Karda. So the outline of the talk is just this follows: introduction, results with some hydrostatic simulations with the regional climate model with the different cumulus schemes, and also simulations with ECMWF era interim reanalysis and GFDL analysis. Then go for results with non-hydrostatic regional climate model, as the regional climate model is having a constant progress from shifting to non-hydrostatic to non-hydrostatic model. So in this we are assessing this mean climatology. Here mainly we are looking for two land surface schemes, BAT and CLM, and also we are looking for some extreme monsoon features in both the simulations, and also some monsoon onset features about these two schemes. Then summary and acknowledgements. So, as you know that summer monsoons, last 3 days we have a lot of talks on Indian summer monsoon importance, because as you know that summer monsoon is contribute more than 70% of its total annual rainfall, which is very important for the people living in these regions. And also have a strong fluctuations during the summer monsoon, which leads to the floods and droughts, which is having a lot of devastating consequences for the country's economy. So as you know that there are many models are using for simulation and prediction of monsoon climate over India and other parts of the globe. So, but if you can see this last 2 decades, regional climate models are coming up with more high resolution climate information than the global climate models. So the regional climate models are also running with the different regions and with high resolution around the globe. So in this study, what we are doing, we are adopting this India regional climate model for the regional scale climate simulations over South Asian regions and Indian regions. You know that regional climate models have developed under downscale since it is the late 1980s and early 90s. Initially, it started with the National Center for Atmospheric Research, and also underwent with a series of development that resulted in successive versions. So out of that, regional REXCM is a regional climate model, is currently developed and maintaining with Abdul Salam International Center for Theoretical Physics, ICTP Italy. This model can be applied for various regions around the world with under the WMO coordinated experiments codex domains, coordinated regional scale domain experiments codex domains. And also this model is having a capability of coupling with the models with ocean, lakes, aerosols, dust, chemistry, hydrology, and land surface processes. So, and also this model is having a very flexibility in using the physical schemes, particularly the cumulus schemes, which can shift over land and ocean, or we can use it. We can call it as a mixed convection schemes. So, in the first part, we are using this model domain of South Asian Codex domain for the regions. This is a Codex domain, and the inner box is we are analyzing more with seasonal scale climate prediction as well as annual cycle climatology. So we are running this model with as a test run. We are running with 1st May 2004. It is already published in the International Journal of Climatology. We are running this model with 45 kilometers horizontal resolution with default land surface schemes of bats and also modified CCM3 radiation parametrization schemes and modified Hortzlog PPL parametrization schemes. And cumulus convections, we are using mainly 4 schemes. One is Grell cumulus and Emmanuel and Titke. And also we are using a combination of Grell and Emmanuel. So Grell we are using over the land and Grell Emmanuel over the land and Grell over the ocean. So these are the common, we can call it as a mixed convection schemes. So, you know, this is big because Emmanuel and these are the schemes. Generally, just I will go very briefly about Emmanuel scheme is when the convection is initiated, when the level of buoyancy is higher than this cloud base. And the Grell scheme and Titke scheme is the mass flux convection schemes, whereas a Grell scheme is triggered when the parcel is lifted in the updraft, eventually reaches the moist convection level. Whereas the Titke scheme is, it uses a number of cloud types as well as cumulus downdroughts that can represent the deep and mid-level and shallow convections. So these are the 3 schemes, and Emmanuel and Grell schemes we are using with the switch Grell Emmanuel over the land and Grell over the oceans, because the Grell scheme is giving the war prediction over the monsoon domain. So here you can see this is the JJS precipitation for the CRU and model simulations. Here we can see black one is CRU observe. We can take the CRU graded data. Red one is Emmanuel and Grell, that is a mixed schemes, and green is Grell schemes, and Titke and Emmanuel schemes, blue and brown. So you can see here throughout this year's model run, the Grell scheme is over-predicted, overestimated. So whereas Emmanuel and Titke is underestimated, but the mixed scheme is giving reasonably a good comparison with the observations. That is CRU observations. Then comes to the annual cycle. You can see blue line is the annual cycle of monthly precipitation for the average of 8 years. You can see the blue line is overestimating. The black line is CRU observations, and red one is GPCP. And Emmanuel and Titke schemes is not showing any monsoon peaks, whereas the Grell scheme and mixed scheme is showing the peak for the monsoon seasons, that is June to September. But if you can see, the mixed scheme is more close to the observations. So this Grell schemes, why it is giving more rainfall during the monsoon seasons? If you can see here the wind pattern, there is a strong cross-equatorial flow over the Arabian Sea, which triggers the heat over the Arabian Sea and transport the water vapor into the Indian landmass and gets more precipitations. This is again observed simulation of temperatures. This black line is the CRU, and green is the mixed convection scheme, and Grell is blue line. You can see here Grell is underestimating the temperature, whereas Emmanuel and Titke is more rainfall, has more temperature, because the rainfall is very less during the monsoon season, so the temperature is more showing in these 2 convection schemes. Whereas the mixed scheme is giving comparingly well with the CRU observations. So then next part, we are going for the two the analysis data sets. One is ERA interim data and one is GFDL. So we compare with two data sets. So what the role of initial conditions, how the monsoon is simulations, because there are plenty of global analysis are available to further downscaling purpose. So we have tested two analysis, GFDL and ERA interim data. You can see the left side here, you can see that this is JJS precipitation for the true observations, and the bottom two are the ERA interim. The left is the ERA interim and GFDL. You can see here the GFDL is more high precipitation over the southern part of India. And the bottom panel, you can see there is less bias in the ERA interim data. So if you can see the bias with respect to CRU observations, and CRU data is more. This is a warm. This is sorry. The dry bias. This is a dry bias for the GFDL rainfall. If you can see the interannual variability, GFDL is giving a more higher precipitation than ERA interim. ERA interim, you can see the left panel. That red bars is ERA interim analysis, simulations with ERA interim analysis, and the green is the GFDL analysis. So the black is the CRU. If you can see here, the red one is more close to the observations than the GFDL analysis. So overall, if you can see, the ERA simulations rainfall is more close with the GFDL. So then again, it is temperature. Temperature also, if you can see, there is more cold bias in the GFDL. Though the two models are giving this cold bias, but the bias is very less in the ERA interim analysis. So similarly, if you can see the interannual variability, you can see the red line is more close to the green line. So the GFDL is very underestimating this. So because of this, you can see the cold bias here. So then we have seen this intra-seasonal variability for the ERA and interim, how these two extreme years are giving the simulating. You can see here ERA is simulating well with the intra-seasonal variability against the GFDL simulations. For example, if you can see 2002, it is a very severe monsoon over India. So ERA interim is giving a reasonably good simulations as compared to the GFDL. GFDL is having very high rainfall over 2002. So this is again, we can see the rainfall and temperature. The green one is CRU. Both ERA and GFDL. If you can see both pictures, ERA interim data is more better in comparable with the observations than GFDL simulations. So in the next part of our study, we are using the ERA interim data, and we have done these two land surface schemes for the long-term simulations. So here we are using this for the Indian regions because of this computational resources here. We have limited to this Indian domain with the non-hydrostatic model, because RxM is having a constant updates and modifications in the RxM 4.7 hours. It is going to be we have options either hydrostatic or non-hydrostatic. In this study, we have taken this non-hydrostatic version, and we run the model with 25 kilometers and 23 vertical levels. And the model is initiated in 1982 to 2016. So here in the previous studies, we found that mixed schemes, that is Emmanuel over land and Grell over the ocean, and boundary layers and radiation schemes we kept constant, and we have switched out two simulations, BATS and CLM. Yeah. So what are the major differences in BATS and CLM? These are the comparison table. BAT is using a 20 vegetation type, and CLM is 24. And the soil temperature is calculating with two-layer force restore method, whereas in the CLM it is having a 10-layer soil model, because in the CLM we are taking 10 unevenly spaced soil layers and 5 snow layers, and with the additional representation of trace and snow. And vegetations we are in the BATS we are treating as that all vegetations with canopy in the same manner. But whereas in the canopy is divided into two types. One is sunlit and shaded fraction, which is a function of leaf area index. And other constants like heat and water vapor, roughness, and prescribed vegetation albedo. These are the constant parameters in the BATS. Whereas in the CLM, it is been calculated with the temporal condenses with both sunlit and shaded fractions, and also this heat and water vapor roughness is updated for the values of bare soil and different vegetation type where it is updating. So these are the two major changes in the BATS and variations in the BATS and the CLM schemes. So again, if you can see the precipitation climatology for the 35 years, you can see both BAT and CLM is giving almost a similar type of structure precipitations, but both are capturing the monsoon features that western part of central Indian regions, the rainfall is it is predicting. But if you can see the difference between this year, we are taking this IMD observations with 0.25 kilometers. If you can see the difference, both are giving this warm this is sorry warm dry bias for the CLM and BATS. But if you can see the difference, CLM is slightly better than the BATS. Okay, but in the western regions, it is the bias is very less, and here the central India it is more bias in the BATS schemes. Okay, if you can see the interannual variations, this black line is the IMD observations, and blue is the CLM, and red is BAT. So if you can see this monsoon season, BAT is giving more higher precipitation during the monsoon seasons than the CLM. But CLM, if you can see, it is more close to the observations, but it is slightly shifted towards monthly shifting is there. If you can see the temperature, we are finding this reverse. So BAT is giving more cold bias, and CLM is giving more.
Now we are 4 minutes only.
Yeah, I'm good. So it is giving more warm bias. This is, but if you can see here, BAT is underestimated and CLM is overestimated. In order to see other winds, I'm skipping here because it is not giving much. Both are simulating very well. Yeah. So then what we have done? We have done some extreme monsoon features. How this year excess years and deficient years are giving the predictions for the both the CLM and BAT schemes. So we have taken 4 excess years and some 8, 9 deficit years, because the last the 4 decades we have this lot of deficient years than the excess monsoon years. So again, if you can see here, the first top panel is the excess monsoon year, and the bottom is deficit years. This is a climatology of excess years. One is difference between BAT and CLM. Right panel is CLM and BAT. So you can see here, excess monsoon year and deficit monsoon year, the bias is very less as compared to the BAT schemes. So it is found that the CLM is more CLM is more good in precipitation for in terms of seasonal, in terms of total precipitation, and also for extreme monsoon cases. So this is again, it is temperature. This is again, as described in the earlier, there is a less bias in the BATs, whereas the CLM is more overestimating. So in order to go for more statistical test, we have done this Taylor diagram. Here we can see here CLM is more close to the reference point, that is IMD. It is in terms of correlation as well as the standard deviation. The CLM is more close. These are the years. Here red points are the BAT and blue is the CLM. For the years, 12 years we have taken this. All the years the CLM is giving better performance than the BAT. So then just I will go other 2-3 slides that I will conclude, sir. So also we have calculated some added value index and modified Periyar skill score. These are the formulas we are using here with the CLM with respect to observations, and modified by the schools 1 minus root mean square error with these conditions. With CLM is less than or equal to BAT. So here you can see here the red color, which indicates it's a positive side, which represents the CLM is better, and if it is more blue color it is there, then it is a BAT is better. So so here you can see this value index. The rainfall climatology for extreme years has a positive values over the central India. Suggests that that CLM is better performance in rainfall simulations, whereas in the temperature case, that blue color is more dominated, which indicates that the BAT scheme is better than CLM. But whereas in the Himalayan regions, so it is reverse in this case.
Can you wind it up?
Yeah. So this is again Periyar skill score for composite of excess and deficit years. Again, this is the same thing to like added value index. Red color shows the better in the CLM scheme, and blue is better in the BAT. You can see here the major portion is the red color, red shaded values, which indicates that CLM is better. So all this statistical technique also it is indicating that CLM is better performance than the BATs, whereas in the temperature case it is CLM is sorry, BAT is better. Yeah. So again, this is my last slide. So again, we have calculated the onset features with both CLM and BAT. Here you can see that this is the top one is the wind field and the bottom one is the rainfall. You can see this answers to all the years from the onset date. We have taken 15 days back and 20 days forward, and we calculated the performance of onset features in the both schemes. So interestingly, both schemes that there is a sharp rise in the. By the way, this is the gridded area. We are taking this monsoon region about the Kerala coast. Similarly, in the bottom panel, the precipitation is also both in the CLM and BATs, it is increasing this one. Okay, but again, you can see here CLM is performing better for the precipitation. Okay, so with this, I summarize my talk. The regional climate models with the mixed convection scheme simulates the summer monsoon precipitation temperature well in terms of spatial distribution and intensity, which is on good agreement with the observations. And ERA interim analysis is giving better performance forced with the regional climate model as initial and boundary conditions than the GFDL analysis. In terms of land surface schemes, both are giving overestimating. However, CLM is slightly closer to the IMD observations. But whereas in the temperature, that BAT is giving better comparison with the observations. And also you can see the annual cycle also, annual cycle as well as statistical analysis. The BAT is giving better agreement with the IMD observations. So, but again, both the schemes, we are using this USGS land surface data. I think a better improvement can be possible with use of Indian land use land cover data for better simulations. So with this, I thank you once again to the organizers for giving this opportunity. This work has been carried out with the support of Ministry of Earth Sciences and the Climate Change Program, Department of Science and Technology, Government of India. Thank you, sir.
Okay, thank you. See, I have got one small question.
Yes, sir.
Have you, see, you know fully well that when we are using different types of models, it has got its own variations. Sometimes it may go very much away from the reality, or it may be very nearer to that. So we have seen that most of the times the models are not one-to-one.
Right, sir.
So have you not tried the ensemble models? That is, you take the somewhat mean of this different type of models, and you know what is ensemble.
Right, sir. Right, sir. Yeah.
So that seems to give a better picture.
Right, sir.
Individual models.
Right, sir. Right, sir. I completely agree with you, sir. But we will attempt those things. But again, because of this computational limitations, we couldn't able to go for so many runs. But at the same time, we are using the CMIP 6 data because we have a lot of more 33 models for the Indian region. But we are already working on that. But again, in this 33 models, 50% of the models are not good for the Indian regions.
That's what I'm telling you. That is the problem.
Yes, yes.
So that from your experience and physical vision about our local regions,
right, sir.
Can you not try for ensemble model by selecting some of the models which you feel that may suit better than the other models, so
right.
that and you come out with your own new model using these things. So,
right, sir.
Okay.
Okay, sir. Thank you, sir.
I don't see any questions from the audience. So let us thank Dr. Raju for his presentation. Thank you. Thank you.
Prashant.
Yes, sir. So I will share my screen.
Okay. I'm happy to see you.
Yeah, I'm also happy, sir. Yeah, seeing after a long time.
Yeah.
Can you see my PPT, sir?
Yes.
Yeah. Okay, sir. So, shall I start?
Sure.
Yes, please.
Okay, sir.
I like to see your presentation.
15 minutes.
Okay, sir.
Sound.
Yes. Yeah. So, good afternoon. Good afternoon, everybody, and thanks for the organizers for giving me a chance to give a invited talk in the INTROMET. So, title of my talk is Impact of Regional Change in Answer Variability on ISMR Predictability, and this is a work I carried out as part of the Monsoon Mission program at IITM.
So from this seminar or from the earlier result, we know that about the monsoon and its importance and how important is the predictability of monsoon and all that things. So here I am dealing with the seasonal prediction of monsoon. We know that what is meant by seasonal prediction. We are predicting a value, seasonal value of anything. For example, ISMR from at least 2 to 3 months ahead or a season ahead. That is mainly the aim of goal of seasonal prediction. So we can see that we have that monsoon mission as part of the monsoon mission. That one model, the CFS climate forecast system, is adopted from NSEP. And as a result of some in-house model development activities, that IMD is using this model as the model for their seasonal prediction. So if you see when the model was in our training period from 1981 to 2002 for the hindcast period, the MMCFS shows a maximum skill of around more than 0.5, around 0.55 at a lead of 3 months. That means that is the model initialized at a February initial condition. It gives a skill of 0.55. And if I compare the model skill with all the other models available at that time, that is from National Multi-Model Ensemble Project of US, and which includes NSEP CFS lower version and NASA models or GFDL models or COLA models or whatever that models, combined with that, our model, that MMCFS at a 3-month lead, is able to give a skill of better skill of around 0.55, and the other models have lesser skill. But still, if the model skill is 0.55, we can see that its interannual variability is less than that of observed, and the potential predictability is very high. It's around 0.7573 like that. So the model needs much improvements, also some improvements. So as part of the in-house improvement activities, something like higher resolution model running and revised convection schemes, and including that the shallow convection schemes, etc., and lot of snow depth, snow modification, etc., works carried out in the IITM. At IITM, give the model ISMR skill is again increased from around 0.7 or 0.65 as part of the in-house activities. So after that, the model is handed over to IMD for the operational use. So here the skill, what I mean is that skill is the just nothing but it's anomaly correlation between the model ISMR. Model ISMR we calculate as the area average rainfall over the Indian land points only, and it's compared with IMD. The anomaly correlation is only called it as the skill here. All this talk, I'm using that anomaly correlation to represent the skill of the model. So the model has a higher skill at a 3-month lead. Then what are the factors is leading to the skill of the model at a 3-month lead time? So that's what we have to check in the next. The left side panel shows that it is a correlation of February, because this is the model is initialized at the month of February. So the February initial SST as correlated with February initial SST is correlated with the observed ISMR in the left figure, and the middle figure, middle panel, we have correlated the model ensemble mean model ensemble mean ISMR is correlated with the February observed February initial SST, and the extreme right panel is what is that for the perfect model assumption. We have taken relative entropy, which will give the perfect model correlation for this. So we can see that the role of February SST in the observed ISMR is almost captured by the model also. So that gives the conclusion that we have a better representation of contribution from initial SST for the February initial condition in the CFS model. And the right figure, it is nothing but it's a correlation of ISMR with the tropical SST. For the first one is observation, and the second one is MMCFS, and all the other models are which I took from the contemporary models of MMCFS, which is from NMME multi-model ensemble group. So we can see that if the compared to observation, this CFS V2 has a PCC, means is a pattern correlation coefficient. The pattern correlation of monsoon teleconnection is maximum for MMCFS compared to all other models. All other models has a correlation of less than 0.5 only, but the monsoon CFS has a correlation of 0.6. So the second point is that it has a better teleconnection during the summer season. And but we can see from the figure that it is more depend on the Pacific SST for its skill. That is okay. That is a drawback of almost all the models. There's a problem with all the models, but still the MMCFS at a 3-month lead has very good representation from initial SST and also better teleconnection during the summer season. So these two factors give MMCFS February IC as a better skill during its training period of 1981 to 2010. Then the next question is that why tropical SST is this much important for representing the ISMR skill? So we can see that the left panel, it is bias, tropical SST bias. Bias means that the difference of model mean JJS mean SST with the observed SST. That may be hard eye SST or some ERA SST, something like that. So we can see that monsoon vision model February IC has the lowest bias in the eastern and in the central Pacific. Whereas if you see any model like a ECMWF model, which has a highest, very high cold bias in the Pacific region. So this monsoon vision and also these NMME models also has the highest cold bias in the Pacific. When we make see the bias of rainfall, we can see that those models who have very high cold bias in the Pacific has very less rainfall bias in the Indian land region. And similarly, if you have the opposite reverse happening here, if you have a less cold bias in the Indian Ocean, we have a very strong dry bias over the monsoon region. So then we just see the annual cycle also. If you see the annual cycle, the first this blue line and red line are the observations from IMD and GPCP, and you can see that monsoon mission February IC is this line. It has the lowest type of annual cycle because it has a long bias is more there, and those models which has a cold bias in the Pacific, suppose something like a ECMWF model which has close to observed annual cycle. So we came to the conclusion that those models which has a cold bias in the Pacific, that models has very less skill for very less dry bias over the Indian land region, and annual cycle is also better for that models. The reason may be this like this: a cold bias in the tropical Pacific will give a La Nina like state already in the model, which will give the intensified circulation over the monsoon region, and it can have an increased rainfall over the monsoon region compared to the models which has a warm bias or no bias at the Pacific. So annual cycle is cycle and mean ISMR is intensified for the models which has a dry bias over the Pacific, which has a cold bias over the Pacific region. So if we come to intra-annual variability, this is the NINO 3.4 influence on the monsoon region in the form of regression. So we can see that when there is a NINO 3.4 will give an, because it's a negative points we have plotted, negatively we have plotted. So it is giving a cold bias, cold SST on this part will give a increased rainfall over the land region. So this is the rainfall structure. So we can see where there is no cold bias or minimum cold bias over the Pacific region, that is like a MMCFS model February IC, which has that teleconnection is captured properly. Whereas the model which has a very cold bias on the Pacific, what will happen is that when there is a cold bias in the Pacific, the circulation has a tendency to shift westwards. So due to that westward shifting, the descent over the monsoon region or the association of the monsoon region is shifted again westward. So we can see that the same SST bias in the Pacific is acting two different ways for the mean state and intra-annual variability of monsoon. Mean, whereas there is a cold bias in the Pacific, mean is improved for ISMR, but its intra-annual variability is decreased when there is a warm cold bias in the Pacific. So that cold Pacific SST has two contrasting effects for mean and intra-annual variability. So in this present model, so with this 10 or 11 models we analyze, we can come to a conclusion that in the present models, Pacific mean state and its teleconnection is very much important for the ISMR prediction in these models. So this is based on the result of 1981 to 2010. But in the recent period, after that period, so in some studies in the early 2020 and all, it has shown that Pacific state has undergone a tremendous change, or that maybe a change has occurred in the Pacific state. So if you see the figures on the left side, the first one is the SST figure, SST standard deviation. This plot is standard deviation, and the shaded is the standard deviation difference between the present state, that means 2000 to 2020 minus 1980 to 2000. So it's a 2 decades difference. So is the shaded one, and condor is the value which is there before 2000, that is 1980 to 2000 times. So we can say that the standard deviation of SST is decreased. The standard deviation means it's intra-annual variability. Intra-annual variability of SST is decreased in the Pacific. Similarly, if you see OLR also, it is also has a decrease in intra-annual variability. Similarly, the H300 is the heat content of the tropical ocean. That is also decreased in the Pacific in the after 2000. So after 2000, ENSO has undergone, or the tropical Pacific has undergone some tremendous changes, which includes the lower interannual variability for ENSO and the periodicity shift from 4 to 7 year to 2 to 3 year. And so due to this, what will happen that subsurface ocean heat content, which has a very good role on the predictability of ENSO, that is also decreased. And the water circulation is intensified because here we have increased convection will come over this region. So water circulation is increased and leading to increased convection over the western part and decreased convection of the eastern part. So it gives that ENSO has undergone some change in the Pacific. So that is a important thing what happened in the 2000. So we know that ENSO is the largest variability in the interannual time scale, and it will affect all over the globe also. So that change how it will affect on the other areas. So if you see the first figure is the ENSO induced pattern for 1980 to 1998, and the second, the right side is that for the recent period. If you can see that the first period, as when the ENSO was stronger like this, it will induce a dipole-like pattern in the Indian Ocean also. But when you have the second period, the ENSO is have a weaker variability that we already discussed. But that ENSO Pacific IOD-like variability in the Indian Ocean is also not there in the time. So if you can see the circulation also, the same change is happening. So earlier times, the circulation over the Pacific was ended just west of the 180-degree date line, and it was a descending over the Mariana continent and the Western Pacific, and it has slight increase over the northwestern Indian Ocean, Western Indian Ocean region. So this is the tripod-like pattern was there. But after the climate shift, after the 2000, what happened is that this warming, because it was a cooling was here. So the warming is that upward motion is shifted towards the east of 180-degree, and that water circulation is shorter, and here is no upward motion or anything in the Indian Ocean. So that kind of variability happened in the Indian Ocean also. When there is a variability happen, there's a change occurred in the Pacific, which is around the year of 2000. So then normally the question is that then what will happen to ENSO predictability? Because even though ENSO variability is decreased, so its predictability also should be affected by that decrease in the variability. So this is a paper by Sang et al. At 2021. What they have shown, this is the lead time predictability or skill of NINO 3.4 index and NINO 3 index. NINO 3.4 and NINO 3 are the indices which we are using to represent the El Nino variability. So we can see that these red lines are all that individual models skill at the period of 1980 to 2000. So the skill is decreasing slowly. And it is by around 10 months, 12 months. So earlier, Dr. Rashav also told that El Nino has a skill of around 12 months. So the skill is decreasing slowly. But if you see the period from 2000 to 2018 or 2020, what happens is that the skill decrease is sharp. So that is the period where we have El Nino has some changes in the Pacific. El Nino basic state itself was changed in the Pacific. According to that, our skill is also decreased for NINO 3.4 and NINO 3. So El Nino skill is also decreased. And the right side figure is that it is a RPSS score for the cold phase, neutral phase, and warm phase of Pacific. That means warm phase is El Nino, cold phase is La Nina. So this also clearly shows that there is a decrease of the predictability for the El Nino in the after 2000. So our point is that El Nino skill is decreased after 2000 for seasonal prediction models. So earlier in the first 2-3 slides, we told that our models, all predictability of ISMR comes from the better representation or the proper representation of El Nino and its teleconnection. So what will be happening to the model? That is our problem. So what will be happening to ISMR? Mainly we are checking in monsoon CFS model only. What will be happening to the ISMR if this kind of changes happen in the Pacific? So this is the first figure. This figure is nothing but it is a 11-year running skill of ISMR from the model. This blue, these lines are for February IC, and the red line is for April IC, and the blue line is for March IC, and the full line is the correlation, that means skill compared to IMD rainfall, and the dotted line is the skill compared to GPCP, because we have to use 1 or 2 data to make sure that whether that is naturally occurring, that is really occurring or not. So here we can see that there is a dip in the around 1995, which we can.
Can you wind it off?
Sir?
Can you wind it off? It is already.
Okay, sir. I'm winding up. So the skill of the ISMR is also decreased when there is after the 2000, the skill of ISMR is also decreased, and similar time the ENSO skill is also decreased. So what I have to say is that this decrease in the skill is natural when we have a model which is initialized at the time of June, before April, the skill decrease is there for El Nino as we observed. But what happened to that is only happening for El Nino for February IC. It is not for all IC. That is our problem. So if you see that observed pattern in the decades, we can see that observed ISMR, this is a correlation of observed ISMR between this observed ISMR for all the tropical SST. We can see that El Nino is increased. At the same time, there is a correlation from Atlantic is also coming. So the models, in reality, ISMR has a good correlation between Pacific Ocean and at the same time Atlantic Ocean after the 2000 period. Before 2000, the Atlantic correlation was very, very insignificant. But after 2000, Atlantic is also coming as a role. So our question is that why the decrease is only for February IC. So I am just concluding fast. So this is a regression of Atlantic index with the tropical rainfall, and this is with the Nino 3. So we can see that the April IC is able to capture the influence of Atlantic SST over the Pacific or the Indian monsoon also. And similarly, the change of El Nino, because El Nino has changed. Because if you see the February IC, its El Nino pattern has no change in the 2 decades. So that April IC is able to capture the change of El Nino pattern, what is naturally occurred, and also the additional contribution from Atlantic Ocean. So February is not able to capture these 2 changes. So that is happened. So this is my conclusion.
Please wait.
Yeah. So ENSO-ISMR relationship is intensified after 2000. Atlantic SSTs also appear as a predictor for ISMR. So if the model capture both these things only, you will have predictability after 2000. February IC failed for this. So our long lead predictability of ISMR is decreased after 2000. That is what the one-line conclusion from this my study. Okay, sir. Thank you.
Okay, thank you. Thank you.
Thank you, Dr. Prashant.
Okay, thank you, sir.
I don't see any questions from audience.
Okay. Okay, thank you.
Thank you.
Professor Toru from Kankawa University.
Okay. So can I share my screen now?
Yeah,
yes, please.
You can share. I am
Sam,
trying to.
will you please?
Yeah.
Yes, sir. I am trying to close my screen, but it is not. I have some problem, sir. I don't know.
Maybe you try to leave the session. Then.
Yes, sir. And now I can. Yeah, it is gone for me. Yeah.
Okay, now I can share my screen.
Yes, Professor Toru. Yes, please share your screen.
Thank you very much.
Thank you. Yeah.
Can you see my screen?
Yes. Yeah.
Okay.
Yeah, you may start. Yes.
Thank you very much. So
and please note that you have 15 minutes to present.
Okay, I try to keep. Yeah.
Yes. Thank you.
And thank you very much. Thank you for inviting me to this very exciting session. And I come from Japan, so we are now launching new ASEAN hydrochromatological project. The name is ASEAPEX, ASEAN Precipitation Experiment. So I like to introduce our project. So it may be related with some predictability of the some long-term predictability of ASEAN monsoon system. So I'd like to join this session. Thank you very much. This is my title and my co-authors here. And maybe as you know, so it is under the WCRP project, and we are now coming up to one of the RHP, kind of a regional hydrochromatological project under US perspective. And so I may skip these slides, maybe you know. And so our project objective is can be summarized as this. So we are now focusing on the ASEAN land precipitation or the terrestrial precipitation in Asia. And it is over the land area. So land has very diverse hydrochromatological conditions. And our project is also aimed for the better prediction and disaster reduction and sustainable development. So it may be very much related with the global warming also. So we are now starting this project just 2 years ago. So now we are now coming up to RHP in UX. We are summarizing our approaches as follows in 6 points. One is observation and estimation of Asia precipitation itself. It's very important for the starting point. And for example, the high mountainous area, the precipitation estimation is very difficult and very coarse and very ambiguous. And some models, some data sets and different data sets shows the different results sometimes. So this is a very important point for us. And second one is the process study of focusing on the land atmosphere coupling. And the third point is the predictability of the time scales between the subseasonal to decadal variability. And the fourth focus is the high resolution hydrological modeling, including human activity, and also the glaciers are very important for the water resources in the area surrounding the glacier areas. And there are so much population there depending on the water resource coming from the glacier areas. So it might be very important point for the hydrological point of view. And the fifth one is a kind of synergy effect to launch good coordinated observational and modeling initiative. And so we are now planning the next observational initiative to research to study about the nature of ASEAN monsoon system and ASEAN hydroclimatical system. And we are now facing on that global warming and its impact on the ASEAN climate is very important issue for the people living in ASEAN area. So the 6th point is placed on the seeking effective and useful climate prediction. So we are now focusing on these 6 points, and many researchers are joining. So some of them are working in some areas like that. So many people are now working in different areas of the research. And usually this type of field activity tend to focus on the regions, but we are now taking not the regional oriented approach, but the approach-oriented research plan. So we are now having these 6 points, and all these 6 points, 6 approaches are covering all the different areas in ASEAN regions. So we can make study for these 6 points, and from these activities, we can clarify the regional aspect of hydroclimatological characteristics. So we are now taking this type of approach-oriented research plan in our ASIAPEX. And in that activity, maybe the 5th point, so the synergy effect or the collaborative observational and modeling initiative is very important for us. So we are thinking about some launching combined observational activity in future. This is one of starting point of our activity. We had a kickoff conference in 2019, August, in Hokkaido, in Japan. And we had researchers from 10 countries, from Philippines, Vietnam, Indonesia, Bangladesh, Mongolia, Nepal, USA, India, and China, and Japan. And we had 61 presentations, and we had a very nice time there. And after that, we had a science steering group workshop, and we are now preparing for one review paper to publish. And we have another activities. This is focusing on South Asia, and ASIAPEC South Asia workshop have been held on 1st to 2nd March 2020 in the Central University of Rajasthan, India. And also we are having several meetings or sessions in the conferences or other congress. And for example, in 2021, we had a AOGS conference. We had a session in AOGS, and we had one of top popular session. So 28 papers have been posted, and we had a very nice chat exchange there. And this is the workshop in Kraj in India. We had a very nice time and some discussion. After that, we had some difficulty facing that the COVID-19, but we are now developing this type of activity. And in the South Asian Meteorological Association also, I am invited to be a speaker, and we have a very good research discussion there. And we are now under the umbrella of JUX and GHP project. So we are now fitting their research focuses. For example, the observation estimation or process studies and predictabilities. And we are conducting the different approach researches, studies, and we can summarize them here. Some of them will be presented. And for example, we are now using the TRIM, the spaceborne radar for our research activity, TRIM, and now it is shifted to GPM. And one of our activity is this. So we are now, Hirose and Okada 2018 has developed a very high, ultra high resolution climatological rainfall estimation in gridded format. And this is already published and also open to the public for using this dataset. This has a 0.01 degree resolution, so it is also 1 kilometer resolution. It covers all the belt area, band area of the globe, and the tropical region is mainly oriented about. So this activity has already been begun, and another research estimated the drop size distribution of the rainfall in the all that area in the world, and including Asia, and using GPM, dual precipitation radar. And the process study is also very much important. And this is one of the example by Teramura et al. 2019. They estimated that how the heterogeneity of surface temperature in the ground surface is important for the formation of mesoscale convective systems. They use the satellite data sets, and they counted how many mesoscale convective systems are formed and in which timing. And also they checked how that these mesoscale convective systems are related with the surface temperature heterogeneity in these areas. And they found that for the northeastern part of ASEAN area, Mongolia, this is northern China, and they're very flat land, but they have some heterogeneity in temperature sometimes. For example, some precipitation system passes in some areas. After that, the soil moisture is different in some area and a different area. And within these two areas, after the sunshine occur, that the temperature heterogeneity develops. So in such a way, we can find some effect of the temperature heterogeneity in the over the land area, and they find that this effect is very important for these areas like this. So this type of process is very important to form the mesoscale convective system in these areas. And also we can find very different type of mesoscalar, some more larger systems. and not necessarily scale, sorry, and the synoptic scale or some other, some larger scales in systems in different areas. So they are, this research focusing on that the Philippines Sea and its effect on the Philippines is clarified by this analysis. And for predictability, also very important things that they have been studied. And Takahashi et al. 2020 have found that the precipitable water increase is very important for the recent future projection of precipitation activity in ASEAN area. Also, Takaya-san has very nice research, conducted very nice research, and they found that some very nice and state-of-the-art recent climate model and its ensemble prediction can catch the very good predictability about the monsoon rainfall in the ASEAN region 1 year ahead. It's very important. And they found that for the key point of this predictability is there on the ENSO activity one, and after that it has impact on the IPOC mode after that. So the reproduction of ENSO and also IPOC mode in that models are very sensitive to get this very good predictability. And so they use a long data set after 1982, a very recent seasons. So they have the very nice result from this analysis. And Hatsuzuka et al. 2020 developed that the future projection of impact of typhoons on the Japan areas. And they found that northern side of Japan have very big impact on the extremity of that rainfall activity in near future by tropical cyclones. And also we are now launching several observational research studies also. One research project is on southern side of Himalayan slope. And Hyplex is very important new project of us. And also Jahe is focusing on the Jakarta area in Indonesia. And also we are now thinking about the larger perspective of observational and modeling initiative. That name is tentatively ASEAN Monsoon Year Second. And now it is some difficult for that the COVID-19. So we are now thinking about that the two phases. One is the some recovery phase, and after that we can have that intensive observation period. So this type of discussion is now just begun. So it's somewhat tentative, but we are not thinking about this type of large-scale observational and modeling initiative. And this is one photo taken in Hokkaido in 2019. So I hope you can join to our activity and a good result. So thank you very much for your focus. Thank you very much.
Okay, thank you, Professor Terao. Are there any questions? None from the audience. Okay. Okay, thank you. Thank you very much, Professor Terao, for your presentation. Yes, thank you.
Next is Dr. Ashok Kumar Das from IMD.
Okay, good afternoon. I thought mine is in the last. Is my screen visible?
Not yet.
I have shared. I have shared it.
Sir, we can see your presentation.
We are not able to see the screen.
Okay.
We can see the screen, but nothing is visible there.
It's blank, right?
Yeah, it's blank.
What? Once green color share screen. It is
Yes.
There. Yes. Then yeah, I shared.
Yeah, now it has come. Yes.
Okay. Thank you. Thank you.
Please put on full screen.
Yeah. Good afternoon. Myself, Dr. Ashok Kumar Das from India Meteorological Department. The title of my study is Performance of GFS in Global Income Model, WRF, and Regional Income for estimation of subbasin-wise quantitative rainfall forecast for Southwest Monsoon 2021 over the Indian regions. Below is our co-authors of this study. The purpose of this paper is to study the performance of the models over river subbasin areas, like the regional models, WRF 3 by 3 kilometer, income 4 by 4 kilometer, then two global models, GFS 12 by 12 kilometer, and income global model 12 by 12 kilometer, and what is its performance over the river subbasin during the Southwest Monsoon season 2021. And regarding data and methodology, model rainfall is taken for each model. We have taken the grid rainfall points which fall within the subbasins are considered for computation of direct model river subbasin wise aerial rainfall. And for this, we have used NCL Anchor Command language for computation of this aerial average rainfall subbasin wise. And for observed rainfall, we have taken daily rainfall data for the stations within the subbasins, and isoidal technique used for this computation of aerial rainfall. We are now having the model rainfall subbasin wise and then observed rainfall over the river subbasin wise. Now, we have actually India Meteorological Department is issuing quantitative precipitation forecast for river subbasins. And as you know, quantitatively rainfall forecast is a very challenge nowadays. We can generally we can say that it is heavy rainfall, yeah, low rainfall. This type of statement we can give, but actually, in what amount of rainfall will occur over a river subbasin is a very challenging till date. So for the support of hydrological forecast, India Meteorological Department issuing quantitative precipitation forecast over river subbasin areas. And these categories are the river subbasin wise, 0, 0.1 to 10, 11 to 25, 26 to 50, 51 to 100, and greater than 100. These are the quantitative precipitation forecast categories. And skill scores for these four models, as I told that four models, we have taken that observed data and forecasted data and prepared a contingency table forecast and based on observation data. And also we have computed the yes/no forecast by converting it to 2x2 contingency table. From the 6x6 contingency table, we have computed skill scores percentage correct, overall percentage correct, and critical success index is computed for each category. If the forecast and the observed rainfall lying within the same category, then we taken as it as correct forecast. Okay, and from the 2x2 contingency table, we have computed probability of detection and false alarm rate. And this is the plant meteorological offices who are issuing the operational quantitative precipitation forecast. To support them, for these four models forecast data, we are downscale to the subbasin scales. And there are 15 flood meteorological offices located at different parts of the country. And there are 153 river subbasins, total 153 river subbasins. This is the boundary as shown in the map. And this is the skill scores. What we have found during the southwest monsoon season 2021. This is for GFS percentage correct overall for 153 river subbasins. For day 1 forecast, it is 56%. Day 2 forecast, it is 54% correct. Then day 3 forecast, it is 53% correct. And day 4 forecast is 51%. And day 5, it is 50% correct for GFS model. And another model, the global income model, its performance a little better. Day 1 forecast, it is 62%. Day 2, it is 60%. And day 3, 58%. Day 4, 56%. And day 5, it is 55%. But whereas in the regional 2 models, the skill scores is very less. Whereas with compared to the global model, it is for WRF, it is 48% day 1, 44% for day 2, and also day 3 it is 44%. For regional income model it is 50%. Again day 2 it is 50% and 48% for day 3. Already I told the GFS model is resolution is 12 kilometer, income also 12 kilometer resolution, whereas this regional model it is WRF 3 by 3 kilometer, income is 4 by 4 kilometer resolution. And this is as you see this from the figure that skill scores is decreasing when we go for the lead time lead time is increasing. And this is the critical success index for each category. What is the performance of the forecast for the rainfall? If you see that 0.1 to 10, it is giving the highest for all models, GFS, WRF, income G, income R. It is only for 0.1 to 10, and then it is decreasing. And if you see the category of greater than 100 category, it is nearing to 0. Means that model performance is decreasing with the increasing of categorical value, sub-basin wise category rainfall value. If the category of the rainfall is increasing, accordingly, the performance also decreasing. And this is probability of detection, similar result like critical success index, the performance is decreasing for her category of rainfall. And this is false alarm rate. You see that if you go for lower to higher categories of rainfall, that false alarm rate is increasing. Means heavy rainfall, false alarm we are issuing means we are estimating higher rainfall categories with compared to observation. Then this is the FMO wise performance of percentage correct. We see that for all FMO, 15 FMOs are there. For below 50% of FMOs observed at Guwahati, Jalpaiguri, Thiruvananthapuram for GFS model. Okay, and all other models are more than 50% percentage correct. For WRF model, it is found that below 50% percentage correct for the FMOs Agra, Asansol, DBC, Guwahati, Jalpaiguri, Patna, Thiruvananthapuram. Okay, this FMO I am telling means there are the river basins under their jurisdiction. Then FMO is for income G, global income model, the below 50% percentage correct is for FMO Guwahati, Jalpaiguri and Thiruvananthapuram. And then FMO below 50% for income regional model, it is below 50% for Ahmedabad, DVG, Guwahati, Jalpaiguri and Thiruvananthapuram. If you see all the models for this Guwahati, Jalpaiguri and Thiruvananthapuram, they are giving for percentage correct 50%, below 50%. And we have studied during the cyclone period how the model performed over the river subbasins. As you know, Gulab and Sahin, cyclone this year monsoon, it is formed. And it is in 24th September, a low pressure area intensified to a well-marked low pressure area and then into deep depression in the same day over East Central Bay of Bengal and its neighborhood. And it's now then moving northwestwards, further intensified into deep depression over north and adjoining central Bay of Bengal in the early morning, and further intensified into cyclonic storm Gulab. And then moving further westwards, it crossed North Andhra Pradesh and adjoining South Odisha, 20 kilometers from Kalingapatnam in 1930 hours IST on 26th September. This is the track of the cyclones. And then the remnant of this cyclone Gulab emerged as a well-marked low pressure area into South Gujarat region and adjoining Gulf and Kambat in the morning of 8:30 hours of 29th September. And it concentrated into a depression over northeast Arabian Sea and adjoining coast in the 5:30 hours of IST in the 30th September. And moving west to northwards, in the it further intensified into a deep depression over the same region in the midnight 23:30 hours IST of 30th September. Thereafter, it moved westwards and intensified into cyclonic storm Sahil over the northeast of Arabian Sea of Gujarat coast. Okay, basically.
Please wind it off. It is only 2 minutes.
Okay. And this is the observation and the model performance. Okay, this is the observation. First panel is the observation, and this is the model forecast. And it is found that the heavy rainfall observed over Lower Godavari forecasted in Sabari, nearby subbasins. It is observed here, Lower Godavari, but it is observed in Sabari. It was forecasted in Sabari. Similarly, the one forecast on 27th by the model income also not properly capturing in the same river subbasins. WRF also not capturing this river subbasin. Nearby subbasin it is observed on 27th September. And 28th October also a similar situation. It is some other basins here showing. And then 29th September, it is over Ahmedabad, the Tapi, Lower Tapi, and Godavari, Narmada, middle and upper Narmada received rainfall, but all the models are showing some higher intensity rainfall, but it is somewhat model is captured. This is my conclusion. PC of model forecast for 153 river subbasin, day 1 to day 5, GFS it is 56, 54, to already I told, and NCAP also it is decreasing, starting from 62. PC of over model forecast for WRF and income, it is 48 to 44% for WRF and NCAP for 50 to 48%. Then PC below 50% already I told, then Guwahati, Jalpaiguri, Thiruvananthapuram, for all models it is showing like this, and CSI POD also decreases, pulse rate also increases as we proceed for lower to higher category of rainfall. PC of all models for FMO Guwahati, Jalpaiguri, Thiruvananthapuram are below 50%, maybe due to the smaller river subbasin areas. And in case of cyclone Gulab, Sahil, there is a positional difference of rainstorm centers over river subbasins along with the track of the cyclone. This may be due to the positional and temporal difference of the synoptic system captured by the model from its actual position and time, which may change the spatial distribution of rainfall as well as temporal distribution of rainfall. Future scope of this model improvement is maybe data assimilation may be used for more data like radar, satellite, AWS data may be assimilated to the model for improving it, and also post-processing technique like batch correction, MOS, AML technique may be used for this improvement of the model. Thank you.
Okay, any questions? If no questions are there, thank you very much.
Thank you, Dr.
Thank
Das.
Thank you, sir. Thank you.
Okay. Next is Dr. Nirupam Karmakar, IIT.
Yes. Hi, everyone. Good afternoon. So I will share my screen now.
Yes, yes, please.
Is it visible?
Yes.
Okay, and I'm completely audible, right? Hello?
Yes, please start.
Okay. Yeah, so I'm Nirupam. I joined
So your audio is not clear.
Okay, so is it
Yeah.
okay now? Okay,
Your
so yeah. Yeah, so I'll be talking about the dynamics that governs the northward propagation of convection during.
Your voice is breaking.
Is it audible now?
No.
Nirupam, there is some problem with the mic connectivity. Probably it may be some loose connection from your end. Can you please check that?
Is it okay now?
Yeah.
Okay. So I'll be talking about the dynamics of northward propagation of convection during boreal summer over Arabian Sea and Bay of Bengal. So these are my contributors.
We are not able to hear you. It's again breaking.
Okay, now can you hear me now?
Yes, now yes, but in between it is breaking the voice.
Okay, I hope it doesn't break further. Okay, so I'll my motivation and objectives. As you can see, the climatological mean May to October rain.
We are not able to hear you.
Okay, can you hear me now?
Yes, yes.
Okay, so the climatological
No, it looks like there is some problem with your microphone or setup.
I think it's not about the volume. It's not about the volume. I think it's about the connectivity. Can you plug it off and again connect it to the microphone?
Yeah, that's what I did. I hope I'm audible now, right?
Yeah, you are audible now.
Okay.
And
so climatological mean.
No, it is breaking again and again. So some issues are there. Why it keeps coming down the volume?
Yeah. Nirupam, it is happening when you move backward.
Yes. Can you hear me now? Can you hear me? Yeah.
So do you have an alternate microphone with you?
Am I audible now?
Yeah, now you can. Yeah, we can hear you now.
Okay. This interseasonal variability of oscillation is one of the most dominant mode of variability in Indian monsoon. It has some distinctive characteristics over Arabian.
Again, it is gone.
some connectivity issues are there. I don't know what is happening.
Dr. Ajil, maybe can we call the next speaker as he solves the problem?
Sir, he is the last speaker.
Is he the last?
Yes, sir. Yes, sir. Yeah.
Okay. Yeah.
Maybe you can. So you can remove the microphone and try directly.
Yeah, I did that, but even that is.
Yeah, you can try using your default microphone on your laptop.
Yeah.
You can use your mobile also. You can talk from mobile and then present from here.
Okay. Yeah.
Okay, don't hurry. Take your time.
Recording.
You have to mute it here.
Yeah.
It is below. It is below.
Ask him to mute on.
Below left. Below left.
Can you hear me from there?
From there itself.
Can you hear me now?
Yes, we can hear you now.
Okay. I'm extremely sorry about this.
No, that is fine. You please. But again, it is coming down. I know.
Okay. Yeah. So, I'll be discussing about the.
Sorry, we are not able to hear you again.
Okay, I hope you can hear me now.
Yes.
Okay. Yeah, so
no, Nirubam, it is gone again. So maybe if you can switch to another computer and wait a couple of minutes, 1 minute.
Okay, so can you give me?
You do one thing, you only show the slides and try to give a small explanation.
Okay.
You can use your mobile phone.
Yeah, so I'll stop sharing for 1 second and then I will join from mobile phone. And Okay, can you hear me now?
Yes.
Okay, so I think this is a better idea. So I will start from the motivation and objectives. So as Bay of Bengal and Arabian Sea, they have very distinctive characteristics of northern propagation from the equatorial region towards the foothills of the Himalayas. I mean, although their mean is different over these two regions, they have a very distinctive characteristics. If you look into the northern propagation of convection in the interseasonal timescale, as interseasonal timescale is one of the dominant mode of variability over Indian summer monsoon. If you look into the phase composite diagrams, which is very popular, very similar to what MGO phase diagrams are shown, this is for Indian monsoon. These different phases are 3 to 5 days apart from each other. This shows that there is a northern propagation of convection from the equatorial region towards the foothills of the Himalayas. Gradually, it develops over this southern tip of West India, and then it propagates towards the north. Now, capturing this northern propagation is very challenging problem, realistically, capturing this northern propagation, and the state-of-the-art models are have very difficulties in simulating this structure of northern propagation, as I mean northern propagation itself, and also the southwest and southeast, northeast, west and tilted structure in it. Now, if we look into the northern propagation over both the ocean basins, Arabian Sea and Bay of Bengal, to understand more about it, we analyzed 1998 to 2014 trim rainfall data and identified few strong convective events associated with the ISO. And we found that there are 63 convective events over Bay of Bengal and 39 over Arabian Sea. Now, if we plot them as a lag latitude diagram, so lag 0 is the day when we have strongest convection maxima over Arabian Sea or Bay of Bengal for this case. Then we see that the northern propagation propagates at a speed of almost 1.25 degrees per day over Arabian Sea. However, over Bay of Bengal, it is 0.74 degrees per day. So this is much slower over Bay of Bengal. Now, there are various studies that have shown that generation of a barotropic vorticity to the north of the convection center is essential for a northern propagation. And in contours, I have shown that the barotropic vertically integrated vorticity. Now it shows a lead of almost 2 to 3 days prior to the convection maxima. So it basically establishes the fact that the barotropic vorticity is essentially playing a role here. Now, what happens with the vorticity budget? We know that the vorticity is important, but can we look further? So in this study, we have started with approximate horizontal momentum equations. So this is the horizontal momentum equations for U and V and the horizontal flow field. And if we have some assumptions that in the presence of background wind, then the interseasonal vorticity equation can be written as this. I mean, with an integration between from the surface to the top of the atmosphere, and then normalized by the G, or the gravitational acceleration. And then we have 4 different terms. The first term is basically the advection. The second one is basically the stretching. Third one, we call it as tilting. And the fourth one is beta. Now, it can be seen that, the terms with the overbar are basically the terms with the background field, and the terms without anything is basically interseasonally filtered fields. It says that changes in the interseasonal vorticity depend upon the modulation of background winds on interseasonally varying flow. Now, if you look into the advection and beta term, so I will just plot each of these terms, advection, tilting, stretching, and beta, in the next 2 slides. And I will show how these terms are basically represented for monsoon, these strong convective events over Bay of Bengal and Arabian Sea. So this basically says this is for Arabian Sea advection, Bay of Bengal advection. And it says that the advection has very less association with the rainfall ISO. However, the beta term shows a very strong association with the rainfall anomalies. Now, in this figure, the colors are basically the vorticity budget terms, and the contours are basically the rainfall plot that I have shown in the first slide. So this basically shows that the beta term basically has a very strong influence on the propagation of northern convection towards north. Now this is negative beta term over Bay of Bengal, and this negative beta term basically leads positive rainfall anomalies during strong convective events by about 5 days, and over Arabian Seas this is not present. So this is a very distinctive characteristics between Arabian Sea and Bay of Bengal, that the beta term actually over Bay of Bengal is present and very strong in nature, and this helps the positive moisture anomalies to advect northward in the direction. There are several theories that actually says that if there is the beta term is very positive, it creates an asymmetry in the meridional velocities, and which basically helps propagate the convection northward. Now, if you look into the tilting and stretching term, this is very interesting. I mean, the tilting term basically shows very interesting characteristics, and over both the ocean basins, tilting leads the rainfall, and over Arabian Sea, it leads by around 2 to 3 days, and over Bay of Bengal, it is 6 to 8 days. This positive tilting anomalies. However, over Arabian Sea, this stretching term, this is the stretching term, is very large in magnitude over northern Arabian Sea as compared to the southern part of it, and over Bay of Bengal, it basically goes along with the precipitation. Now, the stretching term basically is the convergence. If you look into the terms, and this is basically the horizontal convergence that takes into account. So this is basically stretching is basically the horizontal convergence, and that if you look into the lead lag time series over this 10 to 20 north over both the ocean basins, this says that convergence actually goes with the precipitation, but there is a strong peak of tilting terms over Arabian Sea just before the convection maxima. Now, this tilting term is stronger over Bay of Bengal. Now, if you further dissect the tilting term, if you look into the tilting term, there are 4 components in it. The first one I have shown here. If you just plot the first component of this tilting term over Arabian Sea and over Bay of Bengal, the magnitude itself, which says that almost 80% of the tilting is basically contributed by this first component of this tilting term. Now, this basically dominates what is going into the tilting and basically to the vorticity equation. Now, if we look further, this first term consists of 2 components. One is vertical share of mean zonal winds. This is del U del P. If you have continuously stratified atmosphere, this basically represents the vertical share of mean zonal winds. And the other term, the del omega del Y, this basically is the meridional gradient of interseasonal vertical velocity. Now, what does that mean? This is basically if you have a convection, then there is a meridional gradient of vertical velocity. So that basically represents the convection in the atmosphere, and this basically is the mean zonal shear. So I have plotted here the mean zonal shear here, E200 minus U850, which is almost very similar over both the ocean basins. But if you look into the interseasonally filtered vertical velocity, it is more prominent over Bay of Bengal as compared to Arabian Sea, and it is more vertically stretched. So this explains why we have more tilting term, I mean, the stronger tilting term over Bay of Bengal as compared to Arabian Sea. Now, another component is the third component in the tilting term that explains that actually takes into account the meridional vertical share of meridional winds. Now, there are several studies which have shown that the vertical share of meridional winds is important for ISO phase speed. Now, if you look into the meridional vertical share of climatological meridional wind, it shows that there is a positive anomaly over Arabian Sea, but this is negative over Bay of Bengal. So it is very clear that we have a factor that actually can contribute that actually could be playing a role in the differential phase speed of ISO over Arabian Sea and Bay of Bengal. So if this is stronger, if the meridional shear is stronger, they have shown that the ISO actually propagates faster. Now, if you look into the third term, the combined term, this term over Arabian Sea and Bay of Bengal, this basically has a very strong signal over Arabian Sea as expected from the vertical shear figure, but this is a very weak signal over Bay of Bengal. So this basically contributes to the phase speed of ISO over this Arabian Sea. Now, in summary, we have investigated the mechanism of northern propagation of convection over Arabian Sea and Bay of Bengal during boreal summer using a vorticity budget equation. The tilting term basically leads precipitation maximum by about 6 to 8 days over Bay of Bengal and 2 to 3 days over Arabian Sea. Now, the meridional gradient of vertical velocity generates a positive tendency of vorticity to the north of an existing convection. So this basically says that if you have a strong convection, that contributes to the tilting term in the presence of a mean vertical easterly shear, and that creates the barotropic vorticity to the north of a convection, which kind of drags the convection or the low-level moisture convergence to the north of the existing convergence, and hence the north of propagation. Now, its negative values to the south of it actually develop downdrafts and suppresses convection, and this mechanism is very strong over Bay of Bengal. Over Bay of Bengal, this beta term is also very important, but over Arabian Sea, this is relatively weak. And over Arabian Sea, the vertical shear of meridional winds play an important role, and that actually contributes to the faster propagation of Arabian Sea over Arabian Sea. Now, this actually says that the organization of convection could be one of the key components to realistically simulate ISO in models. And this study basically is aimed to develop a diagnostics to provide a pathway when where to look if you want to improve the model to realistically simulate ISO. And this says that the organization of convection is one of the key components here that has to be looked into the models. So this is a part of work that has already been revised in climate dynamics, and thank you for your attention. And this is my contact. If you have any questions, you can take it up now.
Okay, thank you very much.
Thank you, Nirubam.
Thank you. Thank you.
Dr. Anand?
I don't see any questions.
Yeah.
This is the last presentation, right, Dr. Ajit?
Yeah. So can you just wind it up?
Yeah, maybe I can give a short summary and then maybe you can conclude.
You are present.
Okay, so this session on seasonal variability, prediction, and predictability. So we had 6 talks. We had 2 lead talks and 2 invited talks and 2 oral presentations. So the first talk by Professor Ashok was on decadal prediction of IOD. He covered the fundamental aspects and the skills of different models in predicting basically the different phases of IOD, the positive and negative phases of IOD. The second presentation was by Dr. PVS Raju from Amity University. So his talk was on the based on different regional climate model and its performance based on different parameterization schemes. Basically, tested different cumulus parameterization schemes and 2 different land surface schemes and presented the difference in the performance. And the first invited talk was by Dr. Prashant from AITM. We discussed looked at basically the impact of or influence of ENSO prediction skills on the ISMR prediction. And then we had a talk by Professor Toru Terao from Japan. He presented basically the different activities related to the Asian precipitation experiments, which is focusing on 6 science issues like land use, land cover change, the predictability and variability of Asian monsoon, and global warming effect like that. And we had another presentation by Dr. Ashok Kumar Das, comparing the performance and skills of 4 different models. Basically, their performance in the rainfall over the river sub-basins with the objective of providing, improving the flood forecast. The last presentation was by Dr. Nirupam Karmaga from IITM. So he basically looked at the northward propagation of strong convective systems over the Arabian Sea as well as Bay of Bengal by looking at, he explained it using the different terms in the vorticity equation. So we had altogether 6 presentations on this topic. So thank you very much for all the speakers for sharing your findings. Over to Rajan sir. Sir, please.
As Dr. Anand was telling, the total presentation was quite above mark. Everybody has done their part well. They have done real work on different aspects. Hope they will come out with better studies and improvement in the studies which they have done in the coming days. I am quite happy that this session is co-chaired by my close friend plus student plus everything, Dr. Anand. I am seeing him after around 2 years or 3 years.
More than that, sir.
More than that.
Yeah.
So very happy that everything went on very well. Okay, thank you very much.
Thank you. Thank you all.
Thank you. Thank you, sir.
Thank you, sir. Thank you, sir. Thank you. Thank you very much. And we thank Professor C.K. Rajan and Dr. Anand Kumar for chairing the section and effectively managing the presentation. And we also thank all the speakers and audience who have attended online and offline. And there won't be any session in Periyar Hall today, but there will be a special session on National Weather Service at 4:30 in Pampa Hall. I kindly request you all to join for this. Thank you. Thank you very much.